Apollo, the god worship at Delphi, in an Italian 17th century fresco. He first few editions of Mastering Delphi, the best-selling Delphi book I've written, provided an introduction to the Pascal language in Delphi. Due to space constraints and because many Delphi programmers look for more advanced information, in the latest edition this material was completely omitted. To overcome the absence of this information, I've started putting together this book, titled Essential Pascal. This is a detailed book on Pascal, which for the moment will be available for free on my website. This is a work in progress, and any feedback is welcome. The first complete version of this book, dated July '99, has been published on the Delphi 5 Companion CD. Note to the second edition. After a few years, the book had a complete revision, trying to refocus it even more on the core features of the Pascal language. Alongside, the book covers the language from the perspective of the Delphi 4 Windows programmer, but also of the Kylix and Delphi 4 Net programmer. Differences among these different versions of the language will be mentioned. This change in focus was another reason to change most of the examples from visual ones to console-based ones, something I planned doing, but that I still haven't done. Beside the theoretical advantage that the reader can focus even more on the language, ignoring event handlers, methods, component, and other more advanced topics. Only using a console application, the code will be easily portable among the different compilers Borland has made available for Delphi in the recent years. Another change is that I've gone from an HTML-based format to a PDF-based one. With the increased bandwidth people generally have over a few years back, this is really an advantage, and distribution of a single file helps a lot. By the way, the book is now being written with OpenOffice.org. Copyright. The text and the source code of this book is copyrighted by Marco Cantu. Of course, you can use the programs and adapt them to your own needs, only you are not allowed to use them in books, training material, and other copyrighted formats. As you can freely print this book as training material, this doesn't sound like a real restriction to me. Distributing the book is allowed only if no change is applied. Rather than placing a copy of it on your website, though, add a link to the main download site. The reason is that I expect the book to go over frequent changes and updates. Donations. Although the book is available for free to everyone, if you benefit from reading it from a business perspective and if you can afford it, I ask you to donate a small sum to me. As I live on writing and training on programming languages and tool, donation information is available on my website. The currently suggested price is €5. An alternative way of supporting me is to buy one of my books, but in that case I'll get only a limited fraction of the money you spend. Coming to a and the time devoted to update the book. Table of contents. Introduction. 2 Note to the second edition. 2 Copyright. 2 Donations. 2 The book structure. 3 Source code. 5 Feedback. 5 Acknowledgements. 6 About the author. 6 Chapter 1. A short history of the Pascal language. 7 Worse Pascal. 7 Turbo Pascal. 7 Delphi's Pascal. 7 Chapter 2. Coding in Pascal. 9 Comments. 9 Use of upperc as 10 Pretty printing. 11 Syntax highlighting. 1 Using code templates. 12 Language statements. 13 Keywords. 13 Expressions and operators. 16 Conclusion. 17 Chapter 3 Types, Variables, and Constants. 18 Variables. 18 Constants. 19 Resource string constants. 19 Data types. 20 Ordinal types. 20 Real types. 24 Date and time. 25 Specific Windows types. 27 Typecasting and type conversions. 27 Conclusion. 29 Chapter 4 User-defined data types. 30 Named and unnamed types. 30 Subrange types. 31 Enumerated types. 31 Set types. 33 Array types. 34 Record types. 35 Pointers. 36 File types. 38 Conclusion. 38 Chapter 5 Statements. 39 Simple and compound statements. 39 The with statement. 45 Conclusion. 46 Chapter 6 Procedures and functions. 47 Pascal procedures and functions. 47 Reference parameters. 48 Constant parameters. 49 Open array parameters. 49 Delphi calling conventions. 52 What is a method? 53 Forward declarations. 53 Procedural types. 54 Function overloading. 56 Default parameters. 58 C Conclusion. 59 Chapter 7 Handling strings. 60 Types of strings. 60 Using long Strings.60 Looking at strings and memory. 61 Delphi strings and Windows pictures. 62 Formatting strings. 64 Conclusion. 66 Chapter 8 Memory. 67 Dynamic arrays. 67 Conclusion. 69 Chapter 9 Windows Programming. 70 Windows Handles. 70 External Declarations. 71 A Windows Callback Function. 72 Minimal Windows Program. 74 Conclusion. 75 Chapter 1 0 Variants. 76 Variants have no type. 76 Variants in depth. 77 Variants are slow. 78 Conclusion. 79 Chapter 11 Program and Units. 80 Units. 80 Units and Scope. 81 Units as namespaces. 82 Units and Programs. 83 Conclusion. 83 Chapter 12 Files in the Pascal language. 84 Routines for working with files. 84 Handling text files. 85 A text file converter. 86 Saving generic data. 87 From files to streams. 88 Conclusion. 88 Appendix A Glossary. 90 Heap. 90 Stack. Memory. 90 More terms for the glossary. 91. The source code of all the examples mentioned in the book is available. The code has the same copyright as the book. Feel free to use it at will, but don't publish it on other documents or site. Links back to the Essential Pascal site are welcomed. If you go to the site, you can download the source code in a single zip file, epascode.zip, and check out the list of the examples in Appendix B. Feedback. Please let me know of any errors you find, but also of topics not clear enough for a beginner. I'll be able to devote time to the project depending also on the feedback I receive. Let me know also which other topics you'd like to see here. The preferred way of sending feedback is on my public news group in the area devoted to books. If you have troubles using the newsgroups, send an email at the address to marco@marcocantu.com. Acknowledgements. If I'm publishing a book on the web for free, I think this is mainly due to Bruce Eccles' experience with thinking in Java. I'm a friend of Bruce and think he really did a great job with that book and few others. As I mentioned the project to people at Borland, I got a lot of positive feedback as well. And of course I must thank the company for making first the Turbo Pascal series of compilers and now the Delphi series of visual aids. I'm starting to get some precious feedback. The first readers who helped improving this material quite a lot are Charles Wood and Wyatt Wong. Mark Greenhaw helped with some editing of the text. Rafael Barranco Droge offered a lot of technical corrections and language editing. Thanks. About the author. Marco Cantu lives in Piacenza, Italy. After teaching the C++ language and writing C++ and Object Windows library books and articles, in 1995 he delved into Delphi programming. He is the author of the Mastering Delphi book series, published by Cybooks, as well as the Advanced Delphi Developer's Handbook. Marco writes articles for many magazines, including the Delphi magazine, speaks at Delphi and Borland conferences around the world, and teaches Delphi classes at basic and advanced levels. Lately he's getting more and more involved in XML-related technologies, although mostly from the Delphi perspective. You can find more details about Marco and his work on his website. Chapter 1. A Short History of the Pascal Language. The Object Pascal programming language we use in Delphi wasn't invented in 1995 along with the Borland visual development environment. It was simply extended from the Object Pascal language already in use in the Borland Pascal products. But Borland didn't invent Pascal, it only helped make it very popular and extended it a little. Worth's Pascal. The Pascal language was originally designed in 1971 by Niklaus Wirth, professor at the Polytechnic of Zurich, Switzerland. Pascal was designed as a simplified version for educational purposes of the language Algol, which dates from 1960. When Pascal was designed, many programming languages existed, but few were in widespread use: Fortran, C, Assembler, COBOL. The key idea of the new language was order, managed through a strong concept of data type, and requiring declarations and structured program controls. The language was also designed to be a teaching tool for students of programming classes. Turbo Pascal. Borland's world-famous Pascal compiler, called Turbo Pascal, was introduced in 1983, implementing Pascal user manual and report by Jensen and Wirth. The Turbo Pascal compiler has been one of the best-selling series of compilers of all time, and made the language particularly popular on the PC platform, thanks to its balance of simplicity and power. Turbo Pascal introduced an integrated development environment where you could edit the code, run the compiler, see the errors, and jump back to the lines containing those errors. It sounds trivial now, but previously you had to quit the editor, return to DOS, run the command line compiler, write down the error lines, open the editor and jump there. Moreover, Borland sold Turbo Pascal for $49, where Microsoft's Pascal compiler was sold for a few hundred. Turbo Pascal's many years of success contributed to Microsoft's eventual cancellation of its Pascal compiler product. You can actually download a copy of the original version of Borland's Turbo Pascal from the Borland Developers Network website in the Museum section. Delphi's Pascal. After 9 versions of Turbo and Borland Pascal compilers, which gradually extended the language into the OOP realm, Borland released Delphi in 1995, turning Pascal into a visual programming language. Delphi extends the Pascal language in a number of ways, including many object-oriented extensions which are different from other flavors of Object Pascal, including those in the Borland Pascal with Objects compiler. With Delphi 2, Borland brought the Pascal compiler to the 32-bit world, actually re-engineering it to provide a code generator common with the C++ compiler. This brought to the Pascal language many optimizations previously found only in C++ compilers. With Kylix, Borland made a further step and opened to Pascal Delphi programmers a Linux operating system. Most of the examples of this book can be executed almost unchanged on Linux. With the release of version 7 of Delphi, Borland has formally started to name the Pascal language as the Delphi language. So Delphi 7 uses the Delphi language, Kylix 3 supports both the Delphi and the C++ languages, and Borland ships a Delphi language compiler for the Microsoft's .NET architecture. This is mainly a cosmetic and marketing change, probably due to the fact that the Pascal language was never popular in the US as it used to be in Europe and other areas of the world. B. In the listings of the book I'll try to mark comments as italic and keywords in bold, to be consistent with the default Delphi syntax highlighting. Actually, compiler directives are still comments. For example, is legal. It's both a valid directive and a comment, although sane programmers will probably tend to separate directives and comments. Chapter 2. Coding in Pascal. Before we move on to the subject of writing Pascal language statements, it is important to highlight a couple of elements of Pascal coding style. The question I'm addressing here is this: besides the syntax rules, how should you write code? There isn't a single answer to this question, since personal taste can dictate different styles. However, there are some principles you need to know regarding comments, uppercase, spaces, and the so-called pretty printing. In general, the goal of any coding style is clarity. The style and formatting decisions you make are a form of shorthand, indicating the purpose of a given piece of code. An essential tool for clarity is consistency. Whatever style you choose, be sure to follow it throughout a project. Comments. In Pascal, comments are enclosed in either braces or parentheses followed by a star. Delphi also accepts the C++ style comments, which can span to the end of the line. This is a comment up to the end of the line. The first form is shorter and more commonly used. The second form was often preferred in Europe, because many European keyboards lack the brace symbol. The third form of comments has been borrowed from C++ and was added in Delphi 2. Comments up to the end of the line are very helpful for short comments and for commenting out a line of code. Having 3 different forms of comments can be helpful for making nested comments. If you want to comment out several lines of source code to disable them, and these lines contain some real comments, you cannot use the same comment identifier. Code. With a second comment identifier, you can write the following code, which is correct. Code. This comment is okay. Code. Note that if the open brace or parenthesis star is followed by the $sign, it becomes a compiler directive, as in. There is only one exception to the case-insensitive rule of Pascal, the register procedure of a component's package must start with the uppercase R, because of a C++ builder compatibility issue. Use of uppercase. The Pascal compiler ignores the case of characters. Therefore, the identifiers minum, and minum are all exactly equivalent. On the whole, this is definitely a positive, since in case-sensitive languages, many syntax errors are caused by incorrect capitalization. There are a couple of subtle drawbacks, however. First, you must be aware that these identifiers really are the same, so you must avoid using them as different elements. Second, you should try to be consistent in the use of uppercase letters, to improve the readability of the code. A consistent use of case isn't enforced by the compiler, but it is a good habit to get into. A common approach is to capitalize only the first letter of each identifier. When an identifier is made up of several consecutive words, every first letter of a word should be capitalized. My long identifier, me very long, and almost stupid identifier. Other elements completely ignored by the compiler are the spaces, new lines, and tabs you add to the source code. All these elements are collectively known as white space. White space is used only to improve code readability. It does not affect the compilation. Unlike BASIC, Pascal allows you to write a statement on several lines of code, splitting a long instruction on 2 or more lines. The drawback of allowing statements on more than one line is that you have to remember to add a semicolon to indicate the end of a statement, or more precisely, to separate a statement from the next one. Notice that the only restriction in splitting programming statements on different lines is that a string literal may not span several lines. Again, there are no fixed rules on the use of spaces and multiple line statements, just some rules of thumb. The Delphi editor has a vertical line you can place after 60 or 70 characters. If you use this line and try to avoid surpassing this limit, your source code will look better when you print it on paper. Otherwise, long lines may get broken at any position, even in the middle of a word, when you print them. When a function or procedure has several parameters, it is common practice to place the parameters on different lines. You can leave a line completely white before a comment, or to divide a long piece of code in smaller portions. Even this simple idea can improve the readability of the code, both on screen and when you print it. Use spaces to separate the parameters of a function call, and maybe even a space before the initial open parenthesis. Also keep operands of an expression separated. I know that some programmers will disagree with these ideas, but I insist, spaces are free. You don't pay for them. The above formatting is based on pretty printing, but programmers have different interpretations of this general rule. Some programmers indent the begin and end statements to the level of the inner code, some of them indent begin and end, and then indent the internal code once more. Other programmers put the begin in the line of the if condition. This is mostly a matter of personal taste. There are Delphi add-in programs you can use to convert an existing source code to the indentation format you prefer. Pretty printing. The last suggestion on the use of white spaces relates to the typical Pascal language formatting style, known as pretty printing. This rule is simple. Each time you need to write a compound statement, indent it 2 spaces to the right of the rest of the current statement. A compound statement inside another compound statement is indented 4 spaces, and so on. If. Then statement. If. Then begin statement 1. Statement 2. End. If. Then begin if. Then statement 1. Statement 2. End. A similar indented format is often used for lists of variables or data types, and to continue a statement from the previous line. Tip letters equals set of char. Varnam, string. Begin. Masashadolg. Of course. Any such convention is just a suggestion to make the code more readable to other programmers, and it is completely ignored by the compiler. I've tried to use this rule consistently in all of the samples and code fragments in this book. Delphi source code, manuals, and help examples use a similar formatting style. Syntax highlighting. To make it easier to read and write Pascal code, the Delphi editor has a feature called color syntax highlighting. Depending on the meaning in Pascal of the words you type in the editor, they are displayed using different colors. By default, keywords are in bold, strings and comments are in color, and so on. In this book I've tried to apply a sort of syntax highlighting to the source code listings. I hope this actually makes them more readable. Reserved words, comments, and strings are probably the 3 elements that benefit most from this feature. You can see at a glance a misspelled keyword, a string not properly terminated, and the length of a multiple line comment. You can easily customize the syntax highlight settings using the Editor Colors page of the Environment Options dialog box. See Figure 2. 1. If you work by yourself, choose the colors you like. If you work closely with other programmers, you should all agree on a standard color scheme. I find that working on a computer with a different syntax coloring than the one I am used to is really difficult. Figure 2.1. The dialog box used to set the color syntax highlighting. Using code templates. When writing Pascal language statements you often repeat the same sequence of keywords. For this reason, Borland has provided a new feature called code templates. A code template is simply a piece of code related with a shorthand. You type the shorthand, then press Ctrl+J, and the full piece of code appears. For example, if you type arrayed, and then press Ctrl+J, the Delphi editor will expand your text into array of. Since the predefined code templates usually include several versions of the same construct, the shortcut generally terminates with the letter indicating which of the versions you are interested in. However, you can also type only the initial part of the shortcut. For example, if you type R and then press Ctrl+J, the editor will display a local menu with a list of the available choices with a short description, as you can see in Figure 2.2. Figure 2.2, Code Template Selection. You can fully customize the code templates by modifying the existing ones or adding your own common code pieces. If you do this, keep in mind that the text of a code template generally includes the character to indicate where the cursor should jump to after the operation, that is, where you start typing to complete the template with custom code. Language statements. Once you have defined some identifiers, you can use them in statements and in the expressions that are part of some statements. Pascal offers several statements and expressions. Let's look at keywords, expressions, and operators first. Keywords. Keywords are all the Object Pascal reserved identifiers, which have a role in the language. Delphi's help distinguishes between reserved words and directives. Reserved words cannot be used as identifiers, while directives should not be used as such, even if the compiler will accept them. In practice, you should not use any keywords as an identifier. In Table 2.1 you can see a complete list of the identifiers having a specific role in the Object Pascal language, including keywords and other reserved words. Table 2.1, Keywords and other reserved words in the Object Pascal language. Keyword role: absolute directive, abstract directive, and operator. Array type as operator. ASM statement. Assembler backward compatibility. AUT statement. Automated access specifier. Big and block marker KC statement decl function. Calling convention class type const declaration or directive. Constructor special method contents operator. Default directive. Destructor special method disp interface specifier disp interface type div operator DOS statement down DOS statement. Dyna. MAC directive. LC statement. End block marker accept statement. Export backward compatibility. Exports declaration external directive. Far backward compatibility. File type finalization unit. Structure finale statement. For statement forward function directive function declaration go to statement if statement implementation unit. Structure implements directive. In operator, project structure index directive. Inherited statement initialization unit. Structure inline backward compatibility. Interface type ICE operator. Label declaration library program structure Masasha directive. Mid operator. NAMA directive. NAR backward compatibility. Nil value no default directive. NAT operator. Object backward compatibility. Off statement. On statement. OR operator. Out directive. Overload function directive override a foo. Function directive package program structure. Packet directive. Pascal function. Calling convention private access specifier. Procedure declaration program structure property declaration protected access specifier. Public access specifier. Publish shade access specifier. RICE statement. Read property specifier redo. MLI dispatch interface specifier record type register function calling convention reintroduce function directive repeat statement require s program structure. Resident directive. Resource string type safecal function. Calling convention set type SHL operator. SH operator. STDCALLFUNCTION calling convention story directive. String type then statement. 3 advar declaration to statement. TRI statement. Type A declaration unit structure until statement. Contrary to most other programming languages, the AND operators have precedence compared to the relational one. So if you write a less than B and C less than D, the compiler will try to do the AND operation first, resulting in a compiler error. For this reason you should enclose each of the less than expression in parentheses. And use these in its structure var declaration virtual directive. Will a statement with statement write a property specifier write in la dispatch interface specifier XOR operator. Expressions and operators. There isn't a general rule for building expressions, since they mainly depend on the operators being used, and Pascal has a number of operators. There are logical, arithmetic, Boolean, relational, and set operators, plus some others. Expressions can be used to determine the value to assign to a variable, to compute the parameter of a function or procedure, or to test for a condition. Expressions can include function calls, too. Every time you are performing an operation on the value of an identifier, rather than using an identifier by itself, that is an expression. Expressions are common to most programming languages. An expression is any valid combination of constants, variables, literal values, operators, and function results. Expressions can also be passed to value parameters of procedures and functions, but not always to reference parameters. Operators and precedents. If you have ever written a program in your life, you already know what an expression is. Here, I'll highlight specific elements of Pascal operators. You can see a list of the operators of the language, grouped by precedence, in Table 2.2. Some of the common operators have different meanings with different data types. For example, the plus operator can be used to add two numbers, concatenate two strings, make the union of two sets, and even add an offset to a char pointer. However, you cannot add two characters, as is possible in C. Another strange operator is div. In Pascal, you can divide any two numbers with the operator, and you'll invariably get a real number result. If you need to divide two integers and want an integer result, use the div operator instead. Table 2.2, Pascal language operators, grouped by precedence. ANARI operators. Add address of the variable or function. Note Boolean or bitewise not. Multiplicative and bitewise operators. Arithmetic multiplication or set intersection. Floating point division div integer. Division mod modulus. Asalo is a type check type conversion among at runtime. And Boolean or bitewise and shell bitewise left shift sh bitewise right shift additive operators. Plus arithmetic addition, set union, string concatenation. Pointer offset addition. Arithmetic subtraction, set difference. Pointer offset subtraction or Boolean or bitewise or XOR Boolean or bitewise exclusive or relational and comparison operators. Equals test whether equal. Less than greater than test whether not equal. Greater than test whether greater than. Less than equals test whether less than or equal to. Or a subset of a set. Greater than equals test whether greater than or equal to, or a superset of a set in test whether the item is a member of the set is test whether object is type compatible. Set operators. The set operators include union, difference, intersection, membership test, plus some relational operators. To add an element to a set, you can make the union of the set with another one that has only the element you need. Here's a Delphi example related to font styles, style plus. As an alternative, you can use the standard include and exclude procedures, which are much more efficient but cannot be used with component properties of the set type. Because they require an L-value parameter. Include. Conclusion. Now that we know the basic layout of a Pascal program, we are ready to start understanding its meaning in detail. We'll start by exploring the definition of predefined and user-defined data types, then we'll move along to the use of the keywords to form programming statements. Chapter 3 Types, Variables, and Constants. The original Pascal language was based on some simple notions, which have now become quite common in programming languages. The first is the notion of data type. The type determines the values a variable can have, and the operations that can be performed on it. The concept of type is stronger in Pascal than in C, where the arithmetic data types are almost interchangeable, and much stronger than in the original versions of BASIC, which had no similar concept. Variables. Pascal requires all variables to be declared before they are used. Every time you declare a variable, you must specify a data type. Here are some sample variable declarations. var value, integer, is correct, Boolean, a, b, char. The var keyword can be used in several places in the code, such as at the beginning of the code of a function or procedure, to declare variables local to the routine, or inside a unit to declare global variables. After the var keyword comes a list of variable names, followed by a colon and the name of the data type. You can write more than one variable name on a single line, as in the last statement above. Once you have defined a variable of a given type, you can perform on it only the operation supported by its data type. For example, you can use the Boolean value in a test and the integer value in a numerical expression. You cannot mix booleans and integers. Using simple assignments, we can write the following code. Value 10 is correct true. But the next statement is not correct, as the two variables have different data types. Value is correct. Error. If you try to compile this code, Delphi issues a compiler error with this description. Incompatible types, integer and Boolean. Usually, errors like this are programming errors, because it does not make sense to assign a true or false value to a variable of the integer data type. You should not blame Delphi for these errors. It only warns you that there is something wrong in the code. Of course, it is often possible to convert the value of a variable from one type into a different type. In some cases, this conversion is automatic, but usually you need to call a specific system function that changes the internal representation of the data. In Delphi you can assign an initial value to a global variable while you declare it. For example, you can write var value, integer equals 10. Correct, boolean equals true. This initialization technique works only for global variables, not for variables declared inside the scope of a procedure or method. The 16-bit version of Delphi allows you to change the value of a typed constant at runtime, as if it was a variable. The 32-bit version still permits this behavior for backward compatibility when you enable the $J compiler directive, or use the corresponding assignable type constants checkbox of the compiler page of the project options dialog box. This was the default until Delphi 6, but in any case you are strongly advised not to use this trick as a general programming technique. Assigning a new value to a constant disables all the compiler optimizations on constants. In such a case, simply declare a variable, instead. Constants. Pascal also allows a declaration of constants to name values that do not change during program execution. To declare a constant you don't need to specify a data type, but only assign an initial value. The compiler will look at the value and automatically use its proper data type. Here are some sample declarations. Const 1000 equals 1000. Pi equals 3.14. Authorname equals Marco Cantu. Delphi determines the constant data type based on its value. In the example above, the 1000 constant is assumed to be of type smallint, the smallest integral type which can hold it. If you want to tell Delphi to use a specific type you can simply add the type name in the declaration, as in const 1000, integer equals 1000. When you declare a constant, the compiler can choose whether to assign a memory location to the constant, and save its value there, or to duplicate the actual value each time the constant is used. This second approach makes sense particularly for simple constants. Resource string constants. When you define a string constant, instead of writing const authorname equals Marco Cantu, starting with Delphi 3 you can write the following. Resource as string authorname equals Marco Cantu. In both cases you are defining a constant. That is, a value you don't change during program execution. The difference is only in the implementation. A string constant defined with the resources string directive is stored in the resources of the program, in a string table. To see this capability in action, you can look at the Rester example, which has a button with the following code. Resource as string authorname equals Marco Cantu. Bookname equals Essential Pascal. Procedure at form 1. Button 1 click. Begin show message. End. The output of the two strings appears on separate lines because the strings are separated by the new line character. In short, the advantage of resources is in an efficient memory handling performed by Windows and in the possibility of localizing a program without having to modify its source code. Starting with Delphi 6, you can use this Linebreak predefined string for Windows Linux compatibility. The interesting aspect of this program is that if you examine it with a Resource Explorer, you'll see the new strings in the resources. This means that the strings are not part of the compiled code, but stored in a separate area of the executable file. Finally, notice that although this might sound odd, resource strings are available also on Calyx. Data types. In Pascal there are several predefined data types, which can be divided into 3 groups. Ordinal types, real types, and strings. We'll discuss ordinal and real types in the following sections, while strings are covered later in this chapter. In this section I'll also introduce some types defined by the Delphi libraries, which can be considered predefined types. Delphi also includes a non-typed data type, called variant, and discussed in Chapter 10 of this book. Strangely enough, a variant is a type without proper type checking. It was introduced in Delphi 2 to handle all automation. Ordinal types. Ordinal types are based on the concept of order or sequence. Not only can you compare two values to see which is higher, but you can also ask for the value following or preceding a given value or compute the lowest or highest possible value. The 3 most important predefined ordinal types are integer, boolean, and char. However, there are a number of other related types that have the same meaning but a different internal representation and range of values. The following Table 3.1 lists the ordinal data types used for representing numbers. Table 3.1, Ordinal data types for numbers. Sizedesign, Range unsigned, range 8 bits shortened, minus 128 to 127 byte, 0 to 255, 16 bits millind, minus 32,768 to 32,767 word, 0 to 65,535, 32 bits long and, minus 2,147,483,648 to 2,147,483,647 long word, 0 to 4,294,967,295, 64 bits in 64, 16, 32 bits integer cardinal. As you can see, these types correspond to different representations of numbers, depending on the number of bits used to express the value, and the presence or absence of a signed bit. Signed values can be positive or negative, but have a smaller range of values, because one less bit is available for the value itself. You can refer to the range example, discussed in the next section, for the actual range of values of each type. The last group indicates values having a different representation in the 16-bit and 32-bit versions of Delphi. Integer and cardinal are frequently used, because they correspond to the native representation of numbers in the CPU. Integral types. In Delphi 2 and 3, the 32-bit unsigned numbers indicated by the cardinal type were actually 31-bit values, with a range up to 2 GB. Delphi 4 introduced a new unsigned numeric type, long word, which uses a truly 32-bit value up to 4 GB. The cardinal type is now an alias of the long word type. Long word permits 2 GB more data to be addressed by an unsigned number, as mentioned above. Moreover, it corresponds to the native representation of numbers in the CPU. Another new type introduced in Delphi 4 is the int64 type, which represents integer numbers with up to 18 digits. This new type is fully supported by some of the ordinal type routines, numeric routines, and string conversion routines. For the opposite conversion, from a string to a number, there are two new specific functions, strtoint64 and strtoint64def. Boolean. Boolean values other than the Boolean type are seldom used. Some Boolean values with specific representations are required by Windows API functions. The types are bytebool, wordbool, and longbool. In Delphi 3 for compatibility with Visual Basic and OL automation, the data types bytebool, wordbool, and longbool were modified to represent the value true with -1, while the value false is still 0. The Boolean data type remains unchanged. Characters. Finally, there are two different representation for characters, ANSI and WIT-HR. The first type represents 8-bit characters, corresponding to the ANSI character set traditionally used by Windows. The second represents 16-bit characters, corresponding to the new Unicode characters supported by Windows NT, and only partially by Windows 95 and 98. Most of the time you'll simply use the char type, which in Delphi 3 corresponds to ANSI. Keep in mind, anyway, that the first 256 Unicode characters correspond exactly to the ANSI characters. Constant characters can be represented with their symbolic notation, as in K, or with a numeric notation, as in number 78. The latter can also be expressed using the CHR function, as in CHR. The opposite conversion can be done with the OR function. It is generally better to use the symbolic notation when indicating letters, digits, or symbols. When referring to special characters, instead, you'll generally use the numeric notation. The following list includes some of the most commonly used special characters. Number 9 tabulator. Number 10 new line. Number 13 carriage return. The range example. To give you an idea of the different ranges of some of the ordinal types, I've written a simple Delphi program named range. The range program is based on a simple form, which has 6 buttons and some labels for categories of information, as you can see in figure 3. 1. Some of the labels are used to hold static text, others to show the information about the type each time one of the buttons is pressed. Figure 3.1. The range example displays some information about ordinal data types. Every time you press one of the buttons on the right, the program updates the labels with the output. Different labels show the data type, number of bytes used, and the maximum and minimum values the data type can store. Each button has its own on-click event response method because the code used to compute the 3 values is slightly different from button to button. For example, here is the source code of the on-click event for the integer button. Procedure at form range. Integer click. Begin label type. Caption integer. Label size. Captioning toaster. Label max. Captioning toaster. Label min. Captioning toaster. End. If you have some experience with Delphi programming, you can examine the source code of the program to understand how it works. For beginners, it's enough to note the use of three functions: sizeof, high, and low. The results of the last two functions are ordinals of the same type, and the result of the sizeof function is always an integer. The return value of each of these functions is first translated into strings using the intoster function, then copied to the captions of the three labels. The methods associated with the other buttons are very similar to the one above. The only real difference is in the data type passed as a parameter to the various functions. Figure 3.2 shows the result of executing this same program under Windows 95 after it has been recompiled with the 16-bit version of Delphi. Comparing Figure 3.1 with Figure 3.2, you can see the difference between the 16-bit and 32-bit integer data types. Figure 3.2, the output of the 16-bit version of the range example, again showing information about integers. The size of the integer type varies depending on the CPU and operating system you are using. In 16-bit Windows, an integer variable is 2 bytes wide. In 32-bit Windows, an integer is 4 bytes wide. For this reason, when you recompile the range example, you get a different output. The two different representations of the integer type are not a problem, as long as your program doesn't make any assumptions about the size of integers. If you happen to save an integer to a file using one version and retrieve it with another, though, you're going to have some trouble. In this situation, you should choose a platform-independent data type. For mathematical computation or generic code, your best bet is to stick with the standard integral representation for the specific platform, that is, use the integer type, because this is what a CPU likes best. The integer type should be your first choice when handling integer numbers. Use a different representation only when there is a compelling reason to do so. Ordinal types routines. There are some system routines that work on ordinal types. They are shown in Table 3.2. C++ programmers should notice that the two versions of the INC procedure, with one or two parameters, correspond to the ++ and plus equals operators. Table 3.2, System routines for ordinal types. Route purpose-it decrements the variable passed as parameter, by 1 or by the value of the optional second parameter. Inc increments the variable passed as parameter, by 1 or by the specified value. Odd returns true if the argument is an odd number. Pred returns the value before the argument in the order determined by the data type, the predecessor. Suc returns the value after the argument, the successor. Ord returns a number indicating the order of the argument within the set of values of the data type. Low returns the lowest value in the range of the ordinal type passed as its parameter. High returns the highest value in the range of the ordinal data type. Notice that some of these routines, when applied to constants, are automatically evaluated by the compiler and replaced by their value. For example, if you call high where x is defined as an integer, the compiler can simply replace the expression with the highest possible value of the integer data type. Let me explain this better. When you have the integer 23, you can determine which is the following value. Integers are finite. Floating point numbers are infinite even within a small range, and have no order. In fact, how many values are there between 23 and 24? And which number follows 23.46? It is 23.47, 23.461, or 23.4601? That's really hard to know. Real types. Real types represent floating point numbers in various formats. The smallest storage size is given by single numbers, which are implemented with a 4-byte value. Then there are double floating point numbers, implemented with 8 bytes, and extended numbers, implemented with 10 bytes. These are all floating point data types with different precision, which correspond to the IEEE standard floating point representations, and are directly supported by the CPU numeric coprocessor, for maximum speed. In Delphi 2 and Delphi 3 the real type had the same definition as in the 16-bit version. It was a 48-bit type. But its usage was deprecated by Borland, which suggested that you use the single, double, and extended types instead. The reason for their suggestion is that the old 6-byte format is neither supported by the Intel CPU nor listed among the official IEEE real types. To completely overcome the problem, Delphi 4 modifies the definition of the real type to represent a standard 8-byte floating point number. In addition to the advantage of using a standard definition, this change allows components to publish properties based on the real type, something Delphi 3 did not allow. Among the disadvantages there might be compatibility problems. If necessary, you can overcome the possibility of incompatibility by sticking to the Delphi 2 and 3 definition of the type. Do this by using the following compiler option. There are also two strange data types. Comp describes very big integers using 8 bytes. And currency indicates a fixed point decimal value with 4 decimal digits. And the same 64-bit representation as a comp type. As the name implies, the currency data type has been added to handle very precise monetary values, with 4 decimal places. We cannot build a program similar to the range example with real data types, because we cannot use the high and low functions or the ORD function on real type variables. Real types represent an infinite set of numbers. Ordinal types represent a fixed set of values. For this reason, it makes sense to ask for the ordinal position of the character W in the range of the char data type, but it makes no sense at all to ask the same question about 7143. 1562 in the range of a floating point data type. Although you can indeed know whether one real number has a higher value than another, it makes no sense to ask how many real numbers exist before a given number. Real types have a limited role in the user interface portion of the code, but they are fully supported by Delphi, including the database side. The support of IEEE standard floating point types makes the Object Pascal language completely appropriate for the wide range of programs that require numerical computations. If you are interested in this aspect, you can look at the arithmetic functions provided by Delphi in the system unit. Date and time. Delphi uses real types also to handle date and time information. To be more precise, Delphi defines a specific datetime data type. This is a floating point type, because the type must be wide enough to store years, months, days, hours, minutes, and seconds, down to millisecond resolution in a single variable. Dates are stored as the number of days since 1899-12-30 in the integer part of the datetime value. Times are stored as fractions of a day in the decimal part of the value. Datetime is not a predefined type the compiler understands, but it is defined in the system unit as type at datetime equals type double. Using the datetime type is quite easy, because Delphi includes a number of functions that operate on this type. You can find a list of these functions in Table 3.3. Table 3.3, System Routines for the datetime type. Routine description now returns the current date and time into a single datetime value. Data returns only the current date. Time returns only the current time. Data converts a date and time value into a string, using default formatting. To have more control on the conversion, use the format datetime function instead. Data string copies the date and time values into a string buffer, with default formatting. Data converts the date portion of a datetime value into a string. Timitos converts the time portion of a datetime value into a string. Format datetime formats a date and time using the specified format. You can specify which values you want to see and which format to use, providing a complex format string. strctodateTimeconverts a string with date and time information to a datetime value, raising an exception in case of an error in the format of the string. strctodateconverts a string with a date value into the datetime format. strctotimeconverts a string with a time value into the datetime format. Day of week returns the number corresponding to the day of the week of the datetime value passed as parameter. Decode data retrieves the year, month, and day values from a date value. Decode data retrieves out of a time value. Encode data turns year, month, and day values into a datetime value. Encode data turns hour, minute, second, and millisecond values into a datetime value. To show you how to use this data type and some of its related routines, I've built a simple example, named Tomeno. The main form of this example has a button and a list box. Delphi also has a math unit that defines advanced mathematical routines, covering trigonometric functions, finance, and statistics. There are a number of these routines, some of which sound quite strange to me, such as the moment's kurtosis procedure. Component. When the program starts, it automatically computes and displays the current time and date. Every time the button is pressed, the program shows the time elapsed since the program started. Here is the code related to the onCreate event of the form. Procedure form Tomeno. Form create. Begin start time now. Listbox 1. Items. Add. Listbox 1. Items. Add. Listbox 1. Items. Add. End. The first statement is a call to the now function, which returns the current date and time. This value is stored in the start time variable, declared as a global variable as follows. var form Tomeno, start time, date time. I've added only the second declaration, since the first is provided by Delphi. By default, it is the following. var form1, to form1. Changing the name of the form, this declaration is automatically updated. Using global variables is actually not the best approach. It should be better to use a private field of the form class, a topic related to object-oriented programming and discussed in Mastering Delphi 4. The next three statements add 3 items to the listbox component on the left of the form, with the result you can see in Figure 3. 3. The first line contains the time portion of the datetime value converted into a string, the second the date portion of the same value. At the end the code adds a simple reminder. Figure 3.3, the output of the Tomeno example AT startup. This third string is replaced by the program when the user clicks on the elapsed button. Procedure at form Tomeno. But on elapse said click. Vars top time, datetime. Begins top time now. Listbox 1. Items format datetime. End. This code retrieves the new time and computes the difference from the time value stored when the program started. Because we need to use a value that we computed in a different event handler, we had to store it in a global variable. There are actually better alternatives, based on classes. Delphi includes a datetime picker component, which provides a sophisticated way to input a date, selecting it from a calendar. Besides calling to metoster and datatoster, you can use the more powerful format datetime function, as I've done in the last method above. Notice also that time and date values are transformed into strings depending on Windows International settings. Delphi reads these values from the system, and copies them to a number of global constants declared in the sysutils unit. Some of them are date separator, char, short date format, string, long date format, string, time separator, char, time string, string, timepmstring, string, short time format, string, long time format, string, short month names, array 1. 12 of string, long month names, array of string, short day names, array of string, long day names, array of string. More global constants relate to currency and floating point number formatting. You can find the complete list in the Delphi help file under the topic currency and datetime formatting variables. Specific Windows types. The predefined data types we have seen so far are part of the Pascal language. Delphi also includes other data types defined by Windows. These data types are not an integral part of the language, but they are part of the Windows libraries. Windows types include new default types, many records, several pointer types, and so on. Among Windows data types, the most important type is represented by handles, discussed in Chapter 9. Typecasting and type conversions. As we have seen, you cannot assign a variable to another one of a different type. In case you need to do this, there are 2 choices. The first choice is typecasting, which uses a simple functional notation, with the name of the destination data type. Varn, integer. C, char. B, boolean. Begin integer. C char. B boolean. The code that replaces the current value of the third string uses the index 2. The reason is that the items of a list box are 0-based, the first item is number 0, the second number 1, and the third number 2. More on this as we cover arrays. You can typecast between data types having the same size. It is usually safe to typecast between ordinal types, or between real types, but you can also typecast between pointer types. As long as you know what you are doing. Casting, however, is generally a dangerous programming practice, because it allows you to access a value as if it represented something else. Since the internal representations of data types generally do not match, you risk hard-to-track errors. For this reason, you should generally avoid typecasting. The second choice is to use a type conversion routine. The routines for the various types of conversions are summarized in Table 3.4. Some of these routines work on the data types that we'll discuss in the following sections. Notice that the table doesn't include routines for special types, or routines specifically intended for formatting, like the powerful format and format float routines. Table 3.4, System routines for type conversion. Routine description converts an ordinal number into an ANSI character. Ord converts an ordinal type value into the number indicating its order. Round converts a real type value into an integer type value, rounding its value. Trunc converts a real type value into an integer type value, truncating its value. Int returns the integer part of the floating point value argument. Intostr converts a number into a string. IntOx converts a number into a string with its hexadecimal representation. Strtointconverts a string into a number, raising an exception if the string does not represent a valid integer. strtointdefconverts a string into a number, using a default value if the string is not correct. Val converts a string into a number. strconverts a number into a string, using formatting parameters. strpas converts a null-terminated string into a Pascal-style string. This conversion is automatically done for ANSI strings in 32-bit Delphi. strpcopy copies a Pascal-style string into a null-terminated string. This conversion is done with a simple char cast in 32-bit Delphi. strplcopycopies a portion of a Pascal-style string into a null-terminated string. Floatodecimal converts a floating point value to record including its decimal representation. Floatostr converts the floating point value to its string representation using default formatting. Floatostr converts the floating point value to its string representation using the specified formatting. Floatotix copies the floating point value to a string buffer, using the specified formatting. floatotextfmtas a previous routine, copies the floating point value to a string buffer, using the specified formatting. strtofloatconverts the given Pascal string to a floating point value. Text-to-float converts the given null-terminated string to a floating point value. Conclusion. In this chapter we've explored the basic notion of type in Pascal. But the language has another very important feature. It allows programmers to define new custom data types, called user-defined data types. This is a topic of the next chapter. In recent versions of Delphi's Pascal compiler, the round function is based on the FPU processor of the CPU. This processor adopts the so-called banker's rounding, which rounds middle values up and down depending whether they follow an odd or an even number. In general, you should avoid using unnamed types as in the code above, because you cannot pass them as parameters to routines or declare other variables of the same type. The type compatibility rules of Pascal, in fact, are based on type names, not on the actual definition of the types. Two variables of two identical types are still not compatible, unless their types have exactly the same name, and unnamed types are given internal names by the compiler. Get used to defining a data type each time you need a variable with a complicated structure, and you won't regret the time you've spent in it. Chapter 4 User-Defined Data Types. Along with the notion of type, one of the great ideas introduced by the Pascal language is the ability to define new data types in a program. Programmers can define their own data types by means of type constructors, such as subrange types, array types, record types, enumerated types, pointer types, and set types. The most important user-defined data type is the class, which is part of the object-oriented extensions of Object Pascal, not covered in this book. If you think that type constructors are common in many programming languages, you are right, but Pascal was the first language to introduce the idea in a formal and very precise way. There are still few languages with so many mechanisms to define new types. Named and unnamed types. These types can be given a name for later use or applied to a variable directly. When you give a name to a type, you must provide a specific section in the code, such as the following. Type subrange definition uppercase equals A, Z. Array definition temperatures equals array of integer. Record definition date equals record month, byte. Day, byte. Year, integer. End. Enumerated type definition colors equals. Set definition letters equals set of char. Similar type definition constructs can be used directly to define a variable without an explicit type name, as in the following code. var December temperature, array of byte. Color code, array of word. Palette, set of colors. I suggest that you turn on this compiler option while you are developing a program, so it'll be more robust and easier to debug, as in case of errors you'll get an explicit message and not an undetermined behavior. You can eventually disable the option for the final build of the program, to make it a little faster. However, the difference is really small, and for this reason I suggest you to leave all these runtime checks turned on, even in a shipping program. The same holds true for other runtime checking options, such as overflow and stack checking. But what do these type definitions mean? I'll provide some descriptions for those who are not familiar with Pascal type constructs. I'll also try to underline the differences from the same constructs in other programming languages, so you might be interested in reading the following sections even if you are familiar with kind of type definitions exemplified above. Finally, I'll show some Delphi examples and introduce some tools that will allow you to access type information dynamically. Subrange types. A subrange type defines a range of values within the range of another type. You can define a subrange of the integer type, from 1 to 10 or from 100 to 1000, or you can define a subrange of the char type, as in type at n equals 1.10, over 100 equals 100, uppercase equals A, Z. In the definition of a subrange, you don't need to specify the name of the base type. You just need to supply two constants of that type. The original type must be an ordinal type, and the resulting type will be another ordinal type. When you have defined a subrange, you can legally assign it a value within that range. This code is valid for up letter, uppercase, begin up letter F. But this one is not. For up letter, uppercase, begin up letter E. Compile time error. Writing the code above results in a compile time error. Constant expression violates subrange bounds. If you write the following code instead. For up letter, uppercase, letter, char, begin letter, equals single quote E, up letter, Delphi will compile it. At runtime, if you have enabled the range checking compiler option, you'll get a range check error message. Enumerated types can have different internal representations. By default, Delphi uses an 8-bit representation, unless there are more than 256 different values, in which case it uses the 16-bit representation. There is also a 32-bit representation, which might be useful for compatibility with C or C++. Libraries. You can actually change the default behavior, asking for a larger representation, by using the $Z compiler directive. Enumerated types. Enumerated types constitute another user-defined ordinal type. Instead of indicating a range of an existing type, in an enumeration you list all of the possible values for the type. In other words, an enumeration is a list of values. Here are some examples. Typicolors equals. Suit equals. Each value in the list has an associated ordinality, starting with 0. When you apply the ORD function to a value of an enumerated type, you get the 0-based value. For example, ORD returns 1. The Delphi VCL uses enumerated types in many places. For example, the style of the border of a form is defined as follows. Type at from border style equals. When the value of a property is an enumeration, you usually can choose from the list of values displayed in the Object Inspector, as shown in Figure 4.1. Figure 4.1, an enumerated type property in the Object Inspector. The Delphi help file generally lists the possible values of an enumeration. As an alternative, you can use the OR type program, available on to see the list of the values of each Delphi enumeration, set, subrange, and any other ordinal type. You can see an example of the output of this program in Figure 4.2. Figure 4.2, detailed information about an enumerated type, as displayed by the OR type program. Set types. Set types indicate a group of values, where the list of available values is indicated by the ordinal type the set is based onto. These ordinal types are usually limited, and quite often represented by an enumeration or subrange. If we take the subrange 1, 3, the possible values of the set based on it include only 1, only 2, only 3, both 1 and 2, both 1 and 3, both 2 and 3, all the 3 values, or none of them. A variable usually holds one of the possible values of the range of its type. A set type variable, instead, can contain none, 1, 2, 3, or more values of the range. It can even include all of the values. Here is an example of a set. Type letters equals set of uppercase. Now I can define a variable of this type and assign to it some values of the original type. To indicate some values in a set, you write a comma-separated list, enclosed within square brackets. The following code shows the assignment to a variable of several values, a single value, and an empty value. Var letters 1, letters 2, letters 3, letters. Begin letters 1, equals. Letters 2, equals. Letters 3, equals. In Delphi, a set is generally used to indicate non-exclusive flags. For example, the following 2 lines of code declare an enumeration of possible icons for the border of a window and the corresponding set type. Type at border icon equals. Border icons equals set of border icon. In fact, a given window might have none of these icons, one of them, or more than one. When working with the Object Inspector, you can provide the values of a set by expanding the selection and toggling on and off the presence of each value. Figure 4.3, a set type property in the Object Inspector. Another property based on a set type is the style of a font. Possible values indicate a bold, italic, underline, and strike-through font. Of course, the same font can be both italic and bold, have no attributes, or have them all. For this reason it is declared as a set. You can assign values to this set in the code of a program as follows. Font style equals no style font. Style equals bold style only font. Style equals two styles. You can also operate on a set in many different ways, including adding two variables of the same set type. Font style old style plus two sets. Again, you can use the OR type examples included in the tools directory of the book source code to see the list of possible values of many sets defined by the Delphi component library. Array types. Array types define lists of a fixed number of elements of a specific type. You generally use an index within square brackets to access to one of the elements of the array. The square brackets are used also to specify the possible values of the index when the array is defined. For example, you can define a group of 24 integers with this code. Type at temperatures equals array of integer. In the array definition, you need to pass a subrange type within square brackets, or define a new specific subrange type using two constants of an ordinal type. This subrange specifies the valid indexes of the array. Since you specify both the upper and the lower index of the array, the indexes don't need to be zero-based, as is necessary in C, C++, Java, and other programming languages. Since the array indexes are based on subranges, Delphi can check for their range as we've already seen. An invalid constant subrange results in a compile time error, and an out-of-range index used at runtime results in a runtime error if the corresponding compiler option is enabled. Using the array definition above, you can set the value of a datemp1 variable of the datetemperatures type as follows. Type at datetemperatures equals array of integer. var datemp1, datetemperatures. Incidentally, there is no runtime overhead for using low and high with arrays. They are resolved at compile time into constant expressions, not actual function calls. This compile time resolution of expressions and function calls happens also for many other simple system functions. Delphi 4 introduced dynamic arrays into Object Pascal, that is arrays that can be resized at runtime allocating the proper amount of memory. Using dynamic arrays is easy, but in this discussion of Pascal I felt they were not a proper topic to cover. You can find a description of Delphi's dynamic arrays in Chapter 8. Begin datemp1 54, datemp1 52, datemp1 66, datemp1 67. Compile time error. An array can have more than one dimension, as in the following examples. Type month temps equals array of integer. Yardtemps equals array of integer. These two array types are built on the same core types, so you can declare them using the preceding data types, as in the following code. Type month temps equals array of datetemperatures. Yardtemps equals array of month temps. This declaration inverts the order of the indexes as presented above, but it also allows assignment of whole blocks between variables. For example, the following statement copies January's temperatures to February. var this year, yardtemps. Begin this year. You can also define a zero-based array, an array type with the lower bound set to 0. Generally, the use of more logical bounds is an advantage, since you don't need to use the index 2 to access the third item, and so on. Windows, however, uses invariably zero-based arrays. And the Delphi component library tends to do the same. If you need to work on an array, you can always test its bounds by using the standard low and high functions, which return the lower and upper bounds. Using low and high when operating on an array is highly recommended, especially in loops, since it makes the code independent of the range of the array. Later, you can change the declared range of the array indices, and the code that uses low and high will still work. If you write a loop hard-coding the range of an array, you'll have to update the code of the loop when the array size changes. Low and high make your code easier to maintain and more reliable. Delphi uses arrays mainly in the form of array properties. We have already seen an example of such a property in the Tomeno example, to access the items property of a listbox component. I'll show you some more examples of array properties in the next chapter, when discussing Delphi loops. Record types. Record types define fixed collections of items of different types. Each element, or field, has its own type. The definition of a record type lists all these fields, giving each a name you'll use later to access it. Here is a small listing with the definition of a record type, the declaration of a variable of that type, and few statements using this variable. Type a date equals record year, integer, month, byte, day, byte, end. var birthday, date. Begin birthday, year 1997, birthday, month 2, birthday, day 14. Classes and objects can be considered an extension of the record type. Delphi libraries tend to use class types instead of record types, but there are many record types defined by the Windows API. Record types can also have a variant part. That is, multiple fields can be mapped to the same memory area, even if they have a different data type. This corresponds to a union in the C language. Alternatively, you can use these variant fields or groups of fields to access the same memory location within a record, but considering those values from different perspectives. The main uses of this type were to store similar but different data and to obtain an effect similar to that of typecasting. The use of variant record types has been largely replaced by object-oriented and other modern techniques, although Delphi uses them in some peculiar cases. The use of a variant record type is not type-safe and is not a recommended programming practice, particularly for beginners. Expert programmers can indeed use variant record types, and the core of the Delphi libraries makes use of them. You won't need to tackle them until you are really a Delphi expert, anyway. Pointers. A pointer type defines a variable that holds the memory address of another variable of a given data type. So a pointer variable indirectly refers to a value. The definition of a pointer type is not based on a specific keyword, but uses a special character instead. This special symbol is the caret. Type a pointer to equals integer. Once you have defined the pointer variable, you can assign to it the address of another variable of the same type, using the operator. Var, integer, x, integer. Big and bad x. Change the value in two different ways: x10, p20. When you have a pointer p, with the expression p you refer to the address of the memory location the pointer is referring to, and with the expression p you refer to the actual content of that memory location. For this reason in the code fragment above p corresponds to x. Instead of referring to an existing memory location, a pointer can refer to a new memory block dynamically allocated with the new procedure. In this case, when you don't need the pointer anymore, you'll also have to get rid of the memory you've dynamically allocated, by calling the dispose procedure. Var, integer. Begin initialization new. Operations p20. Show message. Termination dispose. End. If a pointer has no value, you can assign the nil value to it. Then you can test whether a pointer is nil to see if it currently refers to a value. This is often used because dereferencing an invalid pointer causes an access violation. Procedure at form. btngpfclick. Var, integer. Big and nil. Show message. End. You can see an example of the effect of this code by running the GPF example. The example contains also the code fragments shown above. Figure 4.4, the system error resulting from the access to a nil pointer, from the GPF example. Although you don't use pointers often in Delphi, you do frequently use a very similar construct, namely, references. Every object instance is really an implicit pointer or reference to its actual data. However, this is completely transparent to the programmer, who uses object variables just like any other data type. Notice also that pointers support will be severely limited in the net version of the Delphi compiler, due to the restrictions imposed by the platform to the so-called safe code. In the same program you can find an example of safe data access. In this second case the pointer is assigned to an existing local variable, and can be safely used, but I've added a suffix anyway. Procedure at form. btnsafeclick. Var, integer. X, integer. Big and bad x. x100. If p less than greater than nil then show message. End. Delphi also defines a pointer data type, which indicates untyped pointers. If you use an untyped pointer you should use getMem instead of new. The getMem procedure is required each time the size of the memory variable to allocate is not defined. The fact that pointers are seldom necessary in Delphi is an interesting advantage of this environment. Nonetheless, understanding pointers is important for advanced programming and for a full understanding of the Delphi object model, which uses pointers behind the scenes. File types. Another Pascal-specific type constructor is the file type. File types represent physical disk files, certainly a peculiarity of the Pascal language. You can define a new file data type as follows. Type int file equals file of integer. Then you can open a physical file associated with this structure and write integer values to it or read the current values from the file. The use of files in Pascal is quite straightforward, but in Delphi there are also some components that are capable of storing or loading their contents to or from a file. There is some serialization support, in the form of streams, and there is also database support. Conclusion. This chapter discussing user-defined data types complete our coverage of Pascal type system. Now we are ready to look into the statements the language provides to operate on the variables we've defined. Files-based examples are covered in a specific chapter. Although these final semicolons serve no purpose, I tend to use them and suggest you do the same. Sometimes after you've written a couple of lines you might want to add one more statement. If the last semicolon is missing you should remember to add it, so it might be better to add it in the first place. By using different symbols for an assignment and an equality test, the Pascal compiler can translate source code faster, because it doesn't need to examine the context in which the operator is used to determine its meaning. The use of different operators also makes the code easier for people to read. Chapter 5 Statements. The data types are one of the foundations of Pascal programming, the other are statements. Statements of the programming language are based on keywords and other elements which allow you to indicate to a program a sequence of operations to perform. Statements are often enclosed in procedures or functions, as we'll see in the next chapter. Now we'll just focus on the basic types of commands you can use to create a program. Simple and compound statements. A Pascal statement is simple when it doesn't contain any other statements. Examples of simple statements are assignment statements and procedure calls. Simple statements are separated by a semicolon. X, Y plus Z. Assignment randomize. Procedure call usually. Statements are part of a compound statement, marked by begin and end brackets. A compound statement can appear in place of a generic Pascal statement. Here is an example. Begin a B. See a 2. End. The semicolon after the last statement before the end isn't required, as in the following. Begin a B. See a 2 end. Both versions are correct. The first version has a useless semicolon. This semicolon is, in fact, a null statement. That is, a statement with no code. Notice that, at times, null statements can be used inside loops or in other particular cases. Assignment statements. Assignments in Pascal use the colon-equal operator, an odd notation for programmers who are used to other languages. The equals operator, which is used for assignments in some other languages, in Pascal is used to test for equality. Conditional statements. A conditional statement is used to execute either one of the statements it contains or none of them, depending on some test. There are two basic flavors of conditional statements, if statements and case statements. If statements. The if statement can be used to execute a statement only if a certain condition is met, or to choose between two different alternatives. The condition is described with a Boolean expression. A simple Delphi example will demonstrate how to write conditional statements. First, create a new application, and put 2 checkboxes and 4 buttons in the form. Do not change the names of buttons or checkboxes, but double-click on each button to add a handler for its on-click event. Here is a simple if statement for the first button. Procedure at form 1. Button 1 click. Begin if checkbox 1. Check then show message. End. When you click on the button, if the first checkbox has a check mark in it, the program will show a simple message, see figure 5. 1. I've used the show message function because it is the simplest Delphi function you can use to display a short message to the user. Figure 5.1. The message displayed by the if test example when you press the first button and the first checkbox is checked. If you click the button and nothing happens, it means the checkbox was not checked. In a case like this, it would probably be better to make this more explicit, as with the code for the second button, which uses an if then else statement. Procedure at form 1. Button 2 click. Begin if then else statement if checkbox 2. Check then. Show message. Else show message. End. Notice that you cannot have a semicolon after the first statement and before the else keyword, or the compiler will issue a syntax error. The if then else statement, in fact, is a single statement, so you cannot place a semicolon in the middle of it. And if statement can be quite complex. The condition can be turned into a series of conditions, or the if statement can nest a second if statement. The last 2 buttons of the if test example demonstrate these cases. Procedure at form 1. Button 3 click. Begin statement with a double condition if checkbox 1. Checked and checkbox 2. Check then show message. End. Procedure at form 1. Button 4 click. Begin compound if statement if checkbox 1. Check then if checkbox 2. Check then show message. Else show message. Else show message. End. Look at the code carefully and run the program to see if you understand everything. When you have doubts about a programming construct, writing a very simple program such as this can help you learn a lot. You can add more checkboxes and increase the complexity of this small example, making any test you like. Case statements. If your if statements become very complex, at times you can replace them with case statements. A case statement consists in an expression used to select a value, a list of possible values, or a range of values. These values are constants, and they must be unique and of an ordinal type. Eventually, there can be an else statement that is executed if none of the labels correspond to the value of the selector. Here are two simple examples. Case number of 1, text 1, 2, text 2, 3, text 3, and case marker of plus, text plus sign, dash, text minus sign, text multiplication or division, single quote 0, 9, text number, A, Z, text lowercase character, A, Z, text uppercase character. The counter of a for loop doesn't need to be a number. It can be a value of any ordinal type, such as a character or an enumerated type. Else a text unknown character. And loops in Pascal. The Pascal language has the typical repetitive statements of most programming languages, including for, while, and repeat statements. Most of what these loops do will be familiar if you've used other programming languages, so I'll cover them only briefly. The for loop. The for loop in Pascal is strictly based on a counter, which can be either increased or decreased each time the loop is executed. Here is a simple example of a for loop used to add the first 10 numbers. Vark, I, integer, begging 0. For I 1 to 10 do kk plus I. This same for statement could have been written using a reverse counter. Vark, I, integer, begging 0. For I 10 down to 1 do kk plus I. The for loop in Pascal is less flexible than in other languages, but it is simple and easy to understand. If you want to test for a more complex condition, or to provide a customized counter, you need to use a while or repeat statement, instead of a for loop. While and repeat statements. The difference between the while loop and the repeat until loop is that the code of the repeat statement is always executed at least once. You can easily understand why by looking at a simple example. While and to begin use I and j to compute something. I plus 1, jj plus 1, and repeat use I and j to compute something. I plus 1. The other key difference between these two loops is that the repeat until loop has a reverse condition. The loop is executed as long as the condition is not met. When the condition is met, the loop terminates. This is the opposite from a while do loop, which is executed while the condition is true. For this reason I had to reverse the condition in the code above to obtain a similar statement. Jj plus 1. Until or. If the initial value of I or j is greater than 100, the statements inside the repeat until loop are executed once anyway. An example of loops. To explore the details of loops, let's look at a small Delphi example. The loops program highlights the difference between a loop with a fixed counter and a loop with an almost random counter. Start with a new blank project, place a list box and 2 buttons on the main form, and give the buttons a proper name by setting their name property in the object inspector. You can also remove the word btn from the caption property. Here is a summary of the textual description of this form. Object form 1, form 1 caption equals loops. Object list box 1, twist box. Object btnfor, button caption equals and for. On click equals btnforclick and object btnwhile, button caption equals and while. On click equals btnwhileclick and end. Figure 5.2, each time you press the for button of the loops example, the list box is filled with consecutive numbers. Now we can add some code to the on-click events of the 2 buttons. The first button has a simple for loop to display a list of numbers, as you can see in figure 5.2. Before executing this loop, which adds a number of strings to the items property of the list box, you need to clear the contents of the list box itself. Procedure at form 1. btnforclick. Vari, integer. Begin list box 1. Items. Clear. For I 1 to 20 do list box 1. Items. Add. End. The code associated with the second button is slightly more complex. In this case, there is a while loop based on a counter, which is increased randomly. To accomplish this, I've called the randomize procedure, which resets the random number generator, and the random function with a range value of 100. The result of this function is a number between 0 and 99, chosen randomly. The series of random numbers control how many times the while loop is executed. Procedure at form 1. btnwhileclick. Vari, integer. Begin list box 1. Items. Clear. Randomize. I0. While I less than 1000 to begin I plus random. List box 1. Items. add, end. Each time you click the while button, the numbers are different, because they depend on the random number generator. Figure 5.3 shows the results from two separate button clicks. Notice that not only are the generated numbers different each time, but so is the number of items. That is, this while loop is executed a random numbers of times. If you press the while button several times in a row, you'll see that the list box has a different number of lines. You can alter the standard flow of a loop's execution using the break and continue system procedures. The first interrupts the loop. The second is used to jump directly to the loop test or counter increment, continuing with the next iteration of the loop. Two more system procedures, exit and halt, let you immediately return from the current function or procedure or terminate the program. Figure 5.3, the contents of the list box of the loop's example change each time you press the while button. The with statement. The last kind of Pascal statement I'll focus on is the with statement, which used to be peculiar to this programming language and can be very useful in Delphi programming. The with statement is nothing but shorthand. When you need to refer to a record type variable, instead of repeating its name every time, you can use a with statement. For example, while presenting the record type, I wrote this code. Type date equals record year, integer, month, byte, day, byte, end. Var birthday, date. Begin birthday, year 1997, birthday, month 2, birthday, day 14. Using a with statement, I can improve the final part of this code, as follows. With birthday due. Begin year 1995, month 2, day 14, end. This approach can be used in Delphi programs to refer to components and other class types. For example, we can rewrite the final part of the last example, loops, using a with statement to access the items of the list box. Procedure at form 1. Will button click. Vari, integer. Begin with list box 1. Items do begin clear. Shortcut randomize. I0. While I less than 1000 to begin I plus random. Shortcut. Add. End. When you work with components or classes in general, the with statement allows you to skip writing some code. Particularly for nested fields. For example, suppose that you need to change the width and the color of the drawing pen for a form. You can write the following code. Form 1. Canvas. Pen. Width 2. Form 1. Canvas. Pen. Color grid. But it is certainly easier to write this code. With Form 1. Canvas. Pen to begin width 2. Color grid. End. When you are writing complex code, the with statement can be effective and spares you the declaration of some temporary variables, but it has a drawback. It can make the code less readable, particularly when you are working with different objects that have similar or corresponding properties. A further drawback is that using the with statement can allow subtle logical errors in the code that the compiler will not detect. For example, with button 1 to begin with 200. Caption new caption. Color grid. End. This code changes the caption and the width of the button, but it affects the color property of the form, not that of the button. The reason is that button components don't have the color property, and since the code is executed for a form object, this object is accessed by default. If we had instead written button 1, width 200, button 1, caption new caption, button 1, color grid, error, the compiler would have issued an error. In general, we can say that since the with statement introduces new identifiers in the current scope, we might hide existing identifiers, or wrongfully access another identifier in the same scope. Even considering this kind of drawback, I suggest you get used to with statements, because they can be really very handy, and at times even make the code more readable. You should, however, avoid using multiple with statements, such as with listbox 1, button 1 do. The code following this would probably be highly unreadable, because for each property defined in this block you would need to think about which component it refers to, depending on the respective properties and the order of the components in the with statement. Speaking of readability, Pascal has no end-if or end-case statement. If an if statement has a begin-end block, then the end of the block marks the end of the statement. The case statement, instead, is always terminated by an end. All these end statements, often found one after the other, can make the code difficult to follow. Only by tracing the indentations can you see which statement a particular end refers to. A common way to solve this problem and make the code more readable is to add a comment after the end statement indicating its role, as in end, if, conclusion. This chapter has described how to code conditional statements and loops. Instead of writing long lists of such statements, programs are usually split in routines, procedures or functions. This is the topic of the next chapter, which introduces also some advanced elements. A. Chapter 6 Procedures and Functions. Another important idea emphasized by Pascal is the concept of the routine, basically a series of statements with a unique name, which can be activated many times by using their name. This way you avoid repeating the same statements over and over, and having a single version of the code you can easily modify it all over the program. From this point of view, you can think of routines as a basic code encapsulation mechanism. I'll get back to this topic with an example after I introduce the Pascal routine syntax. Pascal procedures and functions. In Pascal, a routine can assume two forms, a procedure and a function. In theory, a procedure is an operation you ask the computer to perform, a function is a computation returning a value. This difference is emphasized by the fact that a function has a result, a return value, while a procedure doesn't. Both types of routines can have multiple parameters, of given data types. In practice, however, the difference between functions and procedures is very limited. You can call a function to perform some work and then skip the result, or you can call a procedure which passes a result within its parameters. Here are the definitions of a procedure and two versions of the same function, using a slightly different syntax. Procedure hello, begin show message, end. Function double, integer, begin double value 2, end. Or, as an alternative function double 2, integer, begin result value 2, end. The use of result instead of the function name to assign the return value of a function is becoming quite popular, and tends to make the code more readable, in my opinion. Once these routines have been defined, you can call them one or more times. You call the procedure to make it perform its task, and call a function to compute the value. Procedured form 1. Button 1 click. Begin hello. End. Procedured form 1. Button 2 click. Var. For the moment don't care about the syntax of the two procedures above, which are actually methods. Simply place two buttons on a Delphi form, click on them at design time, and the Delphi IDE will generate the proper support code. Now you simply have to fill in the lines between begin and end. To compile the code above you need to add also an edit control to the form. When you call an existing Delphi function or procedure, or any VCL method, you should remember the number and type of the parameters. Delphi Editor helps you by suggesting the parameters list of a function or procedure with a flyby hint as soon as you type its name and the open parenthesis. This feature is called code parameters and is part of the Code Insight technology. This technique is available in most programming languages. It isn't present in C, but has been introduced in C++, where you use the and symbol. In Visual Basic every parameter not specified as bval is passed by reference. X, Y, integer, begins double, Y double, show message, end. Now we can get back to the encapsulation code concept I've introduced before. When you call the double function, you don't need to know the algorithm used to implement it. If you later find out a better way to double numbers, you can easily change the code of the function, but the calling code will remain unchanged, although executing it will be faster. The same principle can be applied to the hello procedure. We can modify the program output by changing the code of this procedure, and the button 2-click method will automatically change its effect. Here is how we can change the code. Procedure hello. Begin message end. Reference parameters. Pascal routines allow parameter passing by value and by reference. Passing parameters by value is the default. The value is copied on the stack, and the routine uses and manipulates the copy, not the original value. Passing a parameter by reference means that its value is not copied onto the stack in the formal parameter of the routine. Instead, the program refers to the original value, also in the code of the routine. This allows a procedure or function to change the value of the parameter. Parameter passing by reference is expressed by the var keyword. Here is an example of passing a parameter by reference using the var keyword. Procedure double the value. Begin value 2. End. Delphi 3 introduced a new kind of parameter, out. An out parameter has no initial value and is used only to return a value. These parameters should be used only for COM procedures and functions. In general, it is better to stick with the more efficient var parameters. Except for not having an initial value, out parameters behave like var parameters. In this case, the parameter is used both to pass a value to the procedure and to return a new value to the calling code. When you write varx, integer, begins 10, double the value, the value of the x variable becomes 20, because the function uses a reference to the original memory location of x, affecting its initial value. Passing parameters by reference makes sense for ordinal types, for old-fashioned strings, and for large records. Delphi objects, in fact, are invariably passed by value, because they are references themselves. For this reason, passing an object by reference makes little sense, because it corresponds to passing a reference to a reference. Delphi long strings have a slightly different behavior. They behave as references, but if you change one of the string variables referring to the same string in memory, this is copied before updating it. A long string passed as a value parameter behaves as a reference only in terms of memory usage and speed of the operation. But if you modify the value of the string, the original value is not affected. On the contrary, if you pass the long string by reference, you can alter the original value. Constant parameters. As an alternative to reference parameters, you can use a const parameter. Since you cannot assign a new value to a constant parameter inside the routine, the compiler can optimize parameter passing. The compiler can choose an approach similar to reference parameters, but the behavior will remain similar to value parameters, because the original value won't be affected by the routine. In fact, if you try to compile the following code, Delphi will issue an error. Function double the value, integer. Begin value 2. Compiler error result value. End. Open array parameters. Unlike C, a Pascal function or procedure always has a fixed number of parameters. However, there is a way to pass a varying number of parameters to a routine using an open array. The basic definition of an open array parameter is that of a typed open array. This means you indicate the type of the parameter but do not know how many elements of that type the array is going to have. Here is an example of such a definition. Function sum, integer. Var, integer. Typed open arrays are fully compatible with dynamic arrays. Dynamic arrays use the same syntax as open arrays, with the difference that you can use a notation such as array of integer to declare a variable, not just to pass a parameter. Begin result 0. For I low to high do result plus a. End. Using high we can get the size of the array. Notice also the use of the return value of the function, result, to store temporary values. You can call this function by passing to it an array of integer expressions. Xsum. Given an array of integers, of any size, you can pass it directly to a routine requiring an open array parameter or, instead, you can call the slice function to pass only a portion of the array. Here is an example, where the complete array is passed as parameter. Varlist, array of integer. X, I, integer. Begin initialize the array for I low to high to list I2. Call xsum. If you want to pass only a portion of the array to the slice function, simply call it this way. Xsum. You can find all the code fragments presented in this section in the opener example. Figure 6.1, the opener example when the partial slice button is pressed. Do not confuse the var_eq record with the var_data record used by the variant type itself. These two structures have a different aim and are not compatible. Even the list of possible types is different, because var_eq can hold Delphi data types, while var_data can hold all data types. Type variant open array parameters. Besides these typed open arrays, Delphi allows you to define type variant or untyped open arrays. This special kind of array has an undefined number of values, which can be handy for passing parameters. Technically, the construct array of const allows you to pass an array with an undefined number of elements of different types to a routine at once. For example, here is the definition of the format function. Function format, string. The second parameter is an open array, which gets an undefined number of values. In fact, you can call this function in the following ways. N20, stotal. Label 1. Caption format. Label 2. Caption format. Label 3. Caption format. Notice that you can pass a parameter as either a constant value, the value of a variable, or an expression. Declaring a function of this kind is simple, but how do you code it? How do you know the types of the parameters? The values of a type variant open array parameter are compatible with the var_eq type elements. The var_eq record has the following structure. Type at var_eq equals record case byte of integer. Boolean. Char. Extended. VTSTRING. Pointer. VTPCHAR. Object. VTCLASS. TWITHR. VTPWIDECHAR. Inzistering. Currency. Variant. Interface. End. Each possible record has the type field, although this is not easy to see at first because it is declared only once, along with the actual integer size data. Using this information we can actually write a function capable of operating on different data types. In the summl function example, I want to be able to sum values of different types, transforming strings to integers, characters to the corresponding order value, and adding 1 for true Boolean values. The code is based on a case statement, and is quite simple, although we have to dereference pointers quite often. Function summl, extended, var, integer, begin result 0. For I low to high to case args of type of integer, result plus args of integer. Boolean, if args Boolean then result plus 1. Char, result plus ord. Extended, result plus args extended. VTSTRING, string. Result plus STRTOINTDEF, args. VSTRING, 0. Twit result plus ord. Currency, result plus args of currency. End. Case end. I've added this code to the opener example, which calls the summl function when a given button is pressed. Procedure at form 1. Button 4 click. Varx, extended. Y, integer. Begini 10. X summl YY, K, true, 10. 34, 99,999. Show message format. Summl equals greater than %n single quote. End. You can see the output of this call, and the form of the opener example, in Figure 6.2. Figure 6.2, the form of the opener example, with the message box displayed when the untyped button is pressed. Delphi calling conventions. The 32-bit version of Delphi has introduced a new approach to passing parameters, known as fast call. Whenever possible, up to 3 parameters can be passed in CPU registers, making the function call much faster. The fast calling convention is indicated by the register keyword. The problem is that this is the default convention, and functions using it are not compatible with Windows. The functions of the Win32 API must be declared using the stdcall calling convention. A mixture of the original Pascal calling convention of the Win16 API and the decal calling convention of the C language. There is generally no reason not to use a new fast calling convention, unless you are making external Windows calls or defining Windows callback functions. We'll see an example using the stdcall convention before the end of this chapter. You can find a summary of Delphi calling conventions in the calling conventions topic under Delphi Help. What is a method? If you have already worked with Delphi or read the manuals, you have probably heard about the term method. A method is a special kind of function or procedure that is related to a data type, a class. In Delphi, every time we handle an event, we need to define a method, generally a procedure. In general, however, the term method is used to indicate both functions and procedures related to a class. We have already seen a number of methods in the examples in this and the previous chapters. Here is an empty method automatically added by Delphi to the source code of the form. Procedure at form 1. Button 1 click. Begin. End. Forward declarations. When you need to use an identifier, the compiler must have already seen some sort of declaration to know what the identifier refers to. For this reason, you usually provide a full declaration before using any routine. However, there are cases in which this is not possible. If procedure A calls procedure B, and procedure B calls procedure A, when you start writing the code, you will need to call a routine for which the compiler still hasn't seen a declaration. If you want to declare the existence of a procedure or function with a certain name and given parameters, without providing its actual code, you can write the procedure or function followed by the forward keyword. Procedure hello. Forward. Later on, the code should provide a full definition of the procedure, but this can be called even before it is fully defined. Here is a silly example, just to give you the idea. Procedure double hello. Forward. Procedure hello. Begin if message equals nres then double hello else show message. End. Procedure double hello. Begin hello. Hello. End. This approach allows you to write mutual recursion. Double hello calls hello, but hello might call double hello, too. Of course there must be a condition to terminate the recursion, to avoid a stack overflow. You can find this code, with some slight changes, in the double example. Although a forward procedure declaration is not very common in Delphi, there is a similar case that is much more frequent. When you declare a procedure or function in the interface portion of a unit, it is considered a forward declaration, even if the forward keyword is not present. Actually, you cannot write the body of a routine in the interface portion of a unit. At the same time, you must provide in the same unit the actual implementation of each routine you have declared. The same holds for the declaration of a method inside a class type that was automatically generated by Delphi. The event handlers declared inside its form class are forward declarations. The code will be provided in the implementation portion of the unit. Here is an excerpt of the source code of an earlier example, with the declaration of the button one-click method. Type headForm1 equals class. Listbox1, twistbox. Button1, button. Procedure button one-click. End. In the 16-bit version of Delphi, routines must be declared using the for directive in order to be used as actual values of a procedural type. Procedural types. Another unique feature of Object Pascal is the presence of procedural types. These are really an advanced language topic, which only a few Delphi programmers will use regularly. However, since we will discuss related topics in later chapters, it's worth a quick look at them here. If you are a novice programmer, you can skip this section for now, and come back to it when you feel ready. In Pascal, there is the concept of procedural type. The declaration of a procedural type indicates the list of parameters and, in the case of a function, the return type. For example, you can declare a new procedural type, with an integer parameter passed by reference, with this code. Type int_proc equals procedure. This procedural type is compatible with any routine having exactly the same parameters. Here is an example of a compatible routine. Procedure double the value. Begin value 2. End. Procedural types can be used for two different purposes. You can declare variables of a procedural type or pass a procedural type as parameter to another routine. Given the preceding type and procedure declarations, you can write this code. Var int_proc x integer begin double the value x5 ip end. This code has the same effect as the following shorter version. Varx integer begin x5 double the value end. The first version is clearly more complex, so why should we use it? In some cases, being able to decide which function to call and actually calling it later on can be useful. It is possible to build a complex example showing this approach. However, I prefer to let you explore a fairly simple one, named proctype. This example is more complex than those we have seen so far, to make the situation a little more realistic. Simply create a blank project and place two radio buttons and a push button, as shown in Figure 6. 3. This example is based on two procedures. One procedure is used to double the value of the parameter. This procedure is similar to the version I've already shown in this section. Second procedure is used to triple the value of the parameter, and therefore is named triple the value. Figure 6.3, the form of the proctype example. Procedure triple the value. Begin value 3. Show message. End. Both procedures display what is going on, to let us know that they have been called. This is a simple debugging feature you can use to test whether or when a certain portion of code is executed, instead of adding a breakpoint in it. Each time a user presses the apply button, one of the two procedures is executed, depending on the status of the radio buttons. In fact, when you have two radio buttons in a form, only one of them can be selected at a time. This code could have been implemented by testing the value of the radio buttons inside the code for the on-click event of the apply button. To demonstrate the use of procedural types, I've instead used a longer but interesting approach. Each time a user clicks on one of the two radio buttons, one of the procedures is stored in a variable. Procedure headForm1. Double radio button click. Begin double the value. End. When the user clicks on the push button, the procedure we have stored is executed. Procedure headForm1. Apply button click. Begin end. To allow three different functions to access the IP and X variables, we need to make them visible to the whole form. They cannot be declared locally. A solution to this problem is to place these variables inside the form declaration. Type headForm1 equals class. Private. IP, int_proc. X, integer. End. We will see exactly what this means in the next chapter, but for the moment, you need to modify the code generated by Delphi for the class type as indicated above, and add the definition. You can see a practical example of the use of procedural types in Chapter 9, in the section The Windows Callback function. Of the procedural type 1 I've shown before, to initialize these two variables with suitable values, we can handle the onCreate event of the form. I suggest you refer to the listing to study the details of the source code of this example. Function overloading. The idea of overloading is simple. The compiler allows you to define two functions or procedures using the same name, provided that the parameters are different. By checking the parameters, in fact, The compiler can determine which of the versions of the routine you want to call. Consider this series of functions extracted from the math unit of the VCL. Function min, integer, overload. Function min, int64, overload. Function min, single, overload. Function min, double, overload. Function min, extended, overload. When you call min, the compiler easily determines that you're calling the first function of the group, so the return value will be an integer. The basic rules are to: each version of the routine must be followed by the overload keyword. The differences must be in the number or type of the parameters, or both. The return type, instead, cannot be used to distinguish among two routines. Here are 3 overloaded versions of a Showms procedure I've added to the overdef example. Procedure Showms, overload, begin messagedag, end. Procedure Showms, overload, begin messagedag, information, 0, end. Procedure Showms, overload, begin Showms plus str, end. The 3 functions show a message box with a string, after optionally formatting the string in different ways. Here are the 3 calls of the program. Showms, Showms, Showms. What surprised me in a positive way is that Delphi's code parameters technology works very nicely with overloaded procedures and functions. As you type the open parenthesis after the routine name, all the available alternatives are listed. As you enter the parameters, Delphi uses their type to determine which of the alternatives are still available. In figure 6.4 you can see that after starting to type a constant string, Delphi shows only the compatible versions. Figure 6.4, the multiple alternatives offered by code parameters for overloaded routines are filtered according to the parameters already available. The fact that each version of an overloaded routine must be properly marked implies that you cannot overload an existing routine of the same unit that is not marked with the overload keyword. However, you can overload a routine that was originally declared in a different unit. This is for compatibility with previous versions of Delphi, which allow different units to reuse the same routine name. Notice, anyway, that this special case is not an extra feature of overloading, but an indication of the problems you can face. For example, you can add to a unit the following code: procedure messagedag, overload, begin dialogues, messagedag, end. This code doesn't really overload the original messagedag routine. In fact, if you write messagedag, you'll get a nice error message indicating that some of the parameters are missing. The only way to call the local version instead of the one of the VCL is to refer explicitly to the local unit, something that defeats the idea of overloading. Overdef. Messagedag. Default parameters. A related new feature of Delphi 4 is that you can give a default value for the parameter of a function, and you can call the function with or without the parameter. Let me show an example. We can define the following encapsulation of the messagebox method of the application global object, which uses pchar instead of strings, providing 2 default parameters. Procedure messbox. Begin application. Messagebox, pchar, flags, end. With this definition, we can call the procedure in each of the following ways. Messbox. Messbox. Something wrong here. Attention. Messbox. In figure 6.5 you can see that Delphi's code parameters properly use a different style to indicate the parameters that have a default value, so you can easily determine which parameters can be omitted. Figure 6.5, Delphi's code parameters mark out with square brackets the parameters that have default values. You can omit these in the call. Notice that Delphi doesn't generate any special code to support default parameters, nor does it create multiple copies of the routines. The missing parameters are simply added by the compiler to the calling code. There is one important restriction affecting the use of default parameters: you cannot skip parameters. For example, you can't pass the third parameter to the function after omitting the second one. Messbox. Error. This is the main rule for default parameters. In a call, you can only omit parameters starting from the last one. In other words, if you omit a parameter you must omit also the following ones. There are a few other rules for default parameters as well. Parameters with default values must be at the end of the parameters list. Default values must be constants. Obviously, this limits the types you can use with default parameters. For example, a dynamic array or an interface type cannot have a default parameter other than nil. Records cannot be used at all. Default parameters must be passed by value or as const. A reference parameter cannot have a default value. Using default parameters and overloading at the same time can cause quite a few problems, as the two features might conflict. For example, if I add to the previous example the following new version of the Shomes procedure. Procedure Shomes. Overload. Begin message information. 0. End. Then the compiler won't complain this is a legal definition. However, the call Shomes is flagged by the compiler as ambiguous overloaded call to Shomes. Notice that this error shows up in a line of code that compiled correctly before the new overloaded definition. In practice, we have no way to call the Shomes procedure with one string parameter, as the compiler doesn't know whether we want to call the version with only the string parameter or the one with the string parameter and the integer parameter with a default value. When it has a similar doubt, the compiler stops and asks the programmer to state his or her intentions more clearly. Conclusion. Writing procedure and functions is a key element of programming, although in Delphi you'll tend to write methods, procedures and functions connected with classes and objects. Instead of moving on to object-oriented features, however, the next few chapters give you some details on other Pascal programming elements, starting with strings. Chapter 7 Handling Strings. String handling in Delphi is quite simple, but behind the scenes the situation is quite complex. Pascal has a traditional way of handling strings, Windows has its own way, borrowed from the C language, and 32-bit versions of Delphi include a powerful long string data type, which is the default string type in Delphi. Types of strings. In Borland's Turbo Pascal and in 16-bit Delphi, the typical string type is a sequence of characters with a length byte at the beginning, indicating the current size of the string. Because the length is expressed by a single byte, it cannot exceed 255 characters, a very low value that creates many problems for string manipulation. Each string is defined with a fixed size, although you can declare shorter strings to save memory space. A string type is similar to an array type. In fact, a string is almost an array of characters. This is demonstrated by the fact that you can access a specific string character using the notation. To overcome the limits of traditional Pascal strings, the 32-bit versions of Delphi support long strings. There are actually 3 string types. The short string type corresponds to the typical Pascal strings, as described before. These strings have a limit of 255 characters and correspond to the strings in the 16-bit version of Delphi. Each element of a short string is of type ANSI. The ANSI string type corresponds to the new variable length long strings. These strings are allocated dynamically, are reference counted, and use a copy-on-write technique. The size of these strings is almost unlimited. They are also based on the ANSI type. The WID string type is similar to the ANSI string type, but is based on the WID HR type. It stores Unicode characters. Using long strings. If you simply use the string data type, you get either short strings or ANSI strings, depending on the value of the $H compiler directive. $H+ stands for long strings, which is what is used by the components of the Delphi library. Delphi long strings are based on a reference counting mechanism, which keeps track of how many string variables are referring to the same string in memory. This reference counting is used also to free the memory when a string isn't used anymore, that is, when the reference count reaches 0. If you want to increase the size of a string in memory but there is something else in the adjacent memory, then the string cannot grow in the same memory location, and a full copy of the string must therefore be made in another location. When this situation occurs, Delphi's runtime support reallocates the string for you in a completely transparent way. You simply set the maximum size of the string with the setLength procedure, effectively allocating the required amount of memory. SetLength. The setLength procedure performs a memory request, not an actual memory allocation. It reserves the required memory space for future use, without actually using the memory. This technique is based on a feature of the Windows operating systems and is used by Delphi for all dynamic memory allocations. For example, when you request a very large array, its memory is reserved but not allocated. Setting the length of a string is seldom necessary. The only case in which you must allocate memory for the long string using setLength is when you have to pass the string as a parameter to an API function, as I'll show you shortly. Looking at strings and memory. To help you better understand the details of memory management for strings, I've written the simple stref example. In this program I declare 2 global strings, str1 and str2. When the first of the 2 buttons is pressed, the program assigns a constant string to the first of the 2 variables and then assigns the second variable to the first. str1 hello. str2 str1. Besides working on the strings, the program shows their internal status in a list box, using the following string status function. Function string status, string. begin result address, plus int toaster, plus length, plus int toaster, plus references, plus int toaster -8, plus value, plus str, end. It is vital in the string status function to pass the string parameter as a const parameter. Passing this parameter by copying will cause the side effect of having one extra reference to the string while the function is being executed. By contrast, passing the parameter via reference or constant parameter doesn't imply a further reference to the string. In this case I've used the const parameter, as the function is not supposed to modify the string. To obtain the memory address of the string, I've simply made a hard-coded typecast from the string type to the integer type. Strings are references in practice, they're pointers, their value holds the actual memory location of the string. To extract the reference count, I've based the code on the little-known fact that the length and reference count are actually stored in the string, before the actual text and before the position the string variable points to. The offset is -4 for the length of the string and -8 for the reference count. Keep in mind that this internal information about offsets might change in future versions of Delphi. There is also no guarantee that similar undocumented features will be maintained in the future. By running this example, you should get two strings with the same content, the same memory location, and a reference count of 2, as shown in the upper part of the list box of figure 2.1. Now if you change the value of one of the two strings, the memory location of the updated string will change. This is the effect of the copy-on-write technique. Figure 7.1, this graph example shows the internal status of two strings, including the current reference count. We can actually produce this effect, shown in the second part of the list box of figure 7.1, by writing the following code for the onClick event handler of the second button. Procedure at formstref. btnchangeclick. Begin stir 1a. Listbox 1. Items. Add. Listbox 1. Items. Add. Listbox 1. Items. Add. End. Notice that the code of the btnchangeclick method can be executed only after the button click method. To enforce this, the program starts with the second button disabled. It enables the button at the end of the first method. You can freely extend this example and use the string status function to explore the behavior of long strings in many other circumstances. Delphi strings and Windows chars. Another important point in favor of using long strings is that they are null-terminated. This means that they are fully compatible with the C language null-terminated strings used by Windows. A null-terminated string is a sequence of characters followed by a byte that is set to 0. This can be expressed in Delphi using a zero-base array of characters, the data type typically used to implement strings in the C language. This is the reason null-terminated character arrays are so common in the Windows API functions. Since Pascal's long strings are fully compatible with C null-terminated strings, you can simply use long strings and cast them to char when you need to pass a string to a Windows API function. For example, to copy the caption of a form into a char string and then copy it into the caption of the button, you can write the following code. Procedure form 1. Button 1 click. var. s1, string. Begin set length. Get windowtext, length. Button 1. Caption s1. End. You can find this code in the longster example. Note that if you write this code but fail to allocate the memory for the string with such length, the program will probably crash. If you are using a char to pass a value, the code is even simpler, because there is no need to define a temporary string and initialize it. The following line of code passes the caption property of a label as a parameter to an API function, simply by typecasting it to char. Set windowtext. When you need to cast a WID string to a Windows-compatible type, you have to use put-char instead of char for the conversion. WID strings are often used for all and com programs. Having presented the nice picture, now I want to focus on the pitfalls. There are some problems that might arise when you convert a long string into a char. Essentially, the underlying problem is that after this conversion, you become responsible for the string and its contents, and Delphi won't help you anymore. Consider the following limited change to the first program code fragment above. Button 1 click. Procedure at form 1. Button 2 click. vars 1, string. Begin set length. Get windowtext, length. s1 plus is the title. This won't work. Button 1. Caption s1. End. This program compiles, but when you run it, you are in for a surprise. The caption of the button will have the original text of the window title, without the text of the constant string you have added to it. The problem is that when Windows writes to the string, it doesn't set the length of the long Pascal string properly. Delphi still can use this string for output and can figure out when it ends by looking for the null terminator, but if you append further characters after the null terminator, they will be skipped altogether. How can we fix this problem? The solution is to tell the system to convert the string returned by the getWhenDoubtExt API call back to a Pascal string. However, if you write the following code, S1 string, the system will ignore it, because converting a data type back into itself is a useless operation. To obtain the proper long Pascal string, you need to recast the string to a pchar and let Delphi convert it back again properly to a string. S1 string. Actually, you can skip the string conversion, because pchar to string conversions are automatic in Delphi. Here is the final code. Procedure at form 1. Button 3 click. Vars 1, string. Begin set length. GetWhenDoubtExt, length. S1 string. S1 plus is the title. Button 3. Caption S1. End. An alternative is to reset the length of the Delphi string, using the length of the pchar string, by writing set length. You can find 3 versions of this code in the Longster example, which has 3 buttons to execute them. However, if you just need to access the title of a form, you can simply use the caption property of the form object itself. There is no need to write all this confusing code, which was intended only to demonstrate the string conversion problems. There are practical cases when you need to call Windows API functions, and then you have to consider this complex situation. Formatting strings. Using the plus operator and some of the conversion functions, you can indeed build complex strings out of existing values. However, there is a different approach to formatting numbers, currency values, and other strings into a final string. You can use the powerful format function or one of its companion functions. The format function requires as parameters a string with the basic texts and some placeholders and an array of values, one for each placeholder. For example, to format 2 numbers into a string, you can write format, where n1 and n2 are 2 integer values. The first placeholder is replaced by the first value, the second matches the second, and so on. If the output type of the placeholder doesn't match the type of the corresponding parameter, a runtime error occurs. Having no compile time type checking is actually the biggest drawback of using the format function. The format function uses an open array parameter, something I'll discuss toward the end of this chapter. For the moment, though, notice only the array-like syntax of the list of values passed as the second parameter. Besides using %d, you can use one of many other placeholders defined by this function and briefly listed in Table 7.1. These placeholders provide a default output for the given data type. However, you can use further format specifiers to alter the default output. A width specifier, for example, determines a fixed number of characters in the output, while a precision specifier indicates the number of decimal digits. For example, format converts the number n1 into an 8-character string, right aligning the text symbol to specify left justification, filling it with white spaces. Table 7.1, type specifiers for the format function. Types Psi-var description d. The corresponding integer value is converted to a string of decimal digits. X. The corresponding integer value is converted to a string of hexadecimal digits. P. The corresponding pointer value is converted to a string expressed with hexadecimal digits. S. The corresponding string, character, or pchar value is copied to the output string. E. The corresponding floating point value is converted to a string based on exponential notation. F. The corresponding floating point value is converted to a string based on floating point notation. G. The corresponding floating point value is converted to the shortest possible decimal string using either floating point or exponential notation. N. The corresponding floating point value is converted to a floating point string, but also uses thousands separators. M. The corresponding floating point value is converted to a string representing a currency amount. The conversion is based on regional settings. See the Delphi help file under currency and datetime formatting variables. The best way to see examples of these conversions is to experiment with format strings yourself. To make this easier, I've written the FMTest program, which allows a user to provide formatting strings for integer and floating point numbers. As you can see in Figure 7.2, this program displays a form divided into 2 parts. The left part is for integer numbers, the right part for floating point numbers. Each part has a first edit box with the numeric value you want to format to a string. Below the first edit box there is a button to perform the formatting operation and show the result in a message box. Then comes another edit box, where you can type a format string. As an alternative, you can simply click on one of the lines of the listbox component, below, to select a predefined formatting string. Every time you type a new formatting string, It is added to the corresponding list box. Figure 7.2, the output of the floating point value from the FNTest program. The code of this example simply uses the text of the various controls to produce its output. This is one of the 3 methods connected with the show buttons. Procedure at form FNTest. 9 click. Begin show message format edit FNTest. Text. If the item is not there, add it if list box and items. Index of less than 0 then list box and items. Add edit FNTest. Text. End. The code basically does the formatting operation using the text of the edit FNTest edit box and the value of the edit and control. If the format string is not already in the list box, it is then added to it. If the user instead clicks on an item in the list box, the code moves that value to the edit box. Procedure at form FNTest. List box and click. Begin edit FNTest. Text list box and items. End. Conclusion. Strings are certainly a very common data type. Although you can safely use them in most cases without understanding how they work, this chapter should have made clear the exact behavior of strings, making it possible for you to use all the power of this data type. Strings are handled in memory in a special dynamic way, as happens with dynamic arrays. This is the topic of the next chapter. Author's note: this chapter will cover memory handling, discuss the various memory areas, and introduce dynamic arrays. Temporarily only this last part is available. Chapter 8 Memory. Dynamic arrays. Traditionally, the Pascal language has always had fixed-size arrays. When you declare a data type using the array construct, you have to specify the number of elements of the array. As expert programmers probably know, there were a few techniques you could use to implement dynamic arrays, typically using pointers and manually allocating and freeing the required memory. Delphi 4 introduced a very simple implementation of dynamic arrays, modeling them after the dynamic long string type 1 have just covered. As long strings, dynamic arrays are dynamically allocated and reference counted, but they do not offer a copy-on-write technique. That's not a big problem, as you can deallocate an array by setting its variable to nil. You can simply declare an array without specifying the number of elements and then allocate it with a given size using the setLength procedure. The same procedure can also be used to resize an array without losing its content. There are also other string-oriented procedures, such as a copy function, that you can use on arrays. Here is a small code excerpt, underscoring the fact that you must both declare and allocate memory for the array before you can start using it. Procedure at form 1. Button 1 click. var array 1, array of integer. Begin array 1100. Error set length. Array 1100. OK end. As you indicate only the number of elements of the array, the index invariably starts from 0. Generic arrays in Pascal account for a non-zero low bound and for non-integer indexes, 2 features that dynamic arrays don't support. To learn the status of a dynamic array, you can use the length, high, and low functions, as with any other array. For dynamic arrays, however, low always returns 0, and high always returns the length -1. This implies that for an empty array high returns -1. Figure 8.1, the form of the dinar example. After this short introduction I can show you a simple example, called dinar and shown in figure 8. 1. It is indeed simple because there is nothing very complex about dynamic arrays. I'll also use it to show a few possible errors programmers might make. The program declares 2 global arrays and initializes the first in the onCreate handler. var array 1, array 2, array of integer. Procedure at form 1. Form create. Begin allocate set length. End. This sets all the values to 0. This initialization code makes it possible to start reading and writing values of the array right away, without any fear of memory errors. For an even better initialization, the program has a button that writes into each cell of the array. Procedure at form1.btnfillclick. Var integer. Begin for I low to high to array 1I. End. The grow button allows you to modify the size of the array without losing its contents. You can test this by using the get value button after pressing the grow button. Procedure at form1.btngrowclick. Begin grow keeping existing values set length. End. Procedure at form1.btngetclick. Begin extract captioning toaster. End. The only slightly complex code is in the onClick event of the alias button. The program copies one array to the other one with the operator, effectively creating an alias. At this point, however, if you modify one of the arrays, the other is affected as well, as they both refer to the same memory area. Procedure at form1.nolliesclick. Begin alias array2 array1. Change 1. Array2 1000. Show the other caption in toaster. The alias click method does two more operations. The first is an equality test on the arrays. This tests not the actual elements of the structures, but rather the memory areas the arrays refer to, checking whether the variables are two aliases of the same array in memory. Procedure at form1.alias click. Begin. If array1 equals array2, then beep. Truncate first array1 copy. End. The second is a call to the copy function, which not only moves data from one array to the other, but also replaces the first array with a new one created by the function. The effect is that the array1 variable now refers to an array of 11 elements, so that pressing the getValue or setValue buttons produces a memory error and raises an exception. The code of the fill button continues to work fine even after this change, as the items of the array to modify are determined using its current bounds. Conclusion. This chapter temporarily covers only dynamic arrays, certainly an important element for memory management, but only a portion of the entire picture. More material will follow. The memory structure described in this chapter is typical of Windows programming, a topic I'll introduce in the next chapter. Chapter 9 Windows Programming. Delphi provides a complete encapsulation of the low-level Windows API using Object Pascal and the Visual Component Library, so it is rarely necessary to build Windows applications using plain Pascal and calling Windows API functions directly. Nonetheless, programmers who want to use some special techniques not supported by the VCL still have that option in Delphi. You would only want to take this approach for very special cases, such as the development of new Delphi components based on unusual API calls, and I don't want to cover the details. Instead, we'll look at a few elements of Delphi's interaction with the operating system and a couple of techniques that Delphi programmers can benefit from. Windows handles. Among the data types introduced by Windows in Delphi, handles represent the most important group. The name of this data type is handle, and the type is defined in the Windows unit as type at handle equals long word. Handle data types are implemented as numbers, but they are not used as such. In Windows, a handle is a reference to an internal data structure of the system. For example, when you work with a window, the system gives you a handle to the window. The system informs you that the window you are working with is window number 142, for example. From that point on, your application can ask the system to operate on window number 142. Moving it, resizing it, reducing it to an icon, and so on. Many Windows API functions, in fact, have a handle as the first parameter. This doesn't apply only to functions operating on Windows. Other Windows API functions have as their first parameter a GDI handle, a menu handle, an instance handle, a bitmap handle, or one of the many other handle types. In other words, a handle is an internal code you can use to refer to a specific element handled by the system, including a window, a bitmap, an icon, a memory block, a cursor, a font, a menu, and so on. In Delphi, you seldom need to use handles directly, since they are hidden inside forms, bitmaps, and other Delphi objects. They become useful when you want to call a Windows API function that is not supported by Delphi. To complete this description, here is a simple example demonstrating Windows handles. The Wandle program has a simple form, containing just a button. In the code, I respond to the onCreate event of the form and the onClick event of the button, as indicated by the following textual definition of the main form. Object form Wandle caption equals window handle. OnCreate equals formCreate object btncall API, button caption equals call API. OnClick equals btncall API click and end. As soon as the form is created, the program retrieves the handle of the window corresponding to the form. By accessing the handle property of the form itself, we call in toaster to convert the numeric value of the handle into a string, and we append that to the caption of the form, as you can see in figure 9.1. Procedure at form Wandle. Form create. Begin caption plus in toaster. End. Because formCreate is a method of the forms class, it can access other properties and methods of the same class directly. Therefore, in this procedure we can simply refer to the caption of the form and its handle property directly. Figure 9.1, the Wandle example shows the handle of the form window. Every time you run this program you'll get a different value. If you run this program several times you'll generally get different values for the handle. This value, in fact, is determined by Windows and is sent back to the application. Handles are never determined by the program, and they have no predefined values. They are determined by the system, which generates new values each time you run a program. closing parenthesis. When the user presses the button, the program simply calls a Windows API function, setWinDoText, which changes the text or caption of the window passed as the first parameter. To be more precise, the first parameter of this API function is the handle of the window we want to modify. Procedure at form window. BTNCALLAPICLICK. Begins at WinDoText. End. This code has the same effect as the previous event handler, which changed the text of the window by giving a new value to the caption property of the form. In this case, calling an API function makes no sense, because there is a simpler Delphi technique. Some API functions, however, have no correspondence in Delphi, as we'll see in more advanced examples later in the book. External declarations. Another important element for Windows programming is represented by external declarations. Originally used to link the Pascal code to external functions that were written in assembly language, the external declaration is used in Windows programming to call a function from a DLL. In Delphi, there are a number of such declarations in the Windows unit. Forward declaration function Lineto, bool. stdcall. External declaration. Function Lineto. External GDI32.dll, name Lineto. This declaration means that the code of the function Lineto is stored in the GDI32 DLL dynamic library with the same name we are. In the 16-bit version of Delphi, the external declaration used the name of the library without the extension, and was followed by the name directive or by an alternative index directive, followed by the ordinal number of the function inside the DLL. The change reflects a system change in the way libraries are accessed. Although Win32 still allows access to DLL functions by number, Microsoft has stated this won't be supported in the future. Notice also that the Windows unit replaces the WinProx and WinTypes units of the 16-bit version of Delphi. Using in our code, inside an external declaration, in fact, we can specify that our function refer to a function of a DLL that originally had a different name. You seldom need to write declarations like the one just illustrated, since they are already listed in the Windows unit and many other Delphi system units. The only reason you might need to write this external declaration code is to call functions from a custom DLL, or to call undocumented Windows functions. A Windows callback function. We've seen in Chapter 6 that Essential Pascal supports procedural types. A common use of procedural types is to provide callback functions to a Windows API function. First of all, what is a callback function? The idea is that some API function performs a given action over a number of internal elements of the system, such as all of the windows of a certain kind. Such a function, also called an enumerated function, requires as a parameter the action to be performed on each of the elements, which is passed as a function or procedure compatible with a given procedural type. Windows uses callback functions in other circumstances, but we'll limit our study to this simple case. Now consider the enum Windows API function, which has the following prototype. Bool enum Windows. Enum proclpenum func, address of callback function lparam application defines value. Of course, this is the C language definition. We can look inside the Windows unit to retrieve the corresponding Pascal language definition. Function enum Windows. Lpenum func, tfnwndenumproc. Lparam, bool. stdcall. Consulting the help file, we find that the function passed as a parameter should be of the following type. Bool callback enum Windows proc. hwnd, handle of parent window param application define value. This corresponds to the following Delphi procedural type definition. Type enum Windows proc equals function, boolean, stdcall. The first parameter is the handle of each main window in turn, while the second is the value we've passed when calling the enum Windows function. Actually in Pascal the tfnwndenumproc type is not properly defined. It is simply a pointer. This means we need to provide a function with the proper parameters and then use it as a pointer, taking the address of. Windows requires programmers to follow the stdcall calling convention every time we call a Windows API function or pass a callback function to the system. Delphi, by default, uses a different and more efficient calling convention, indicated by the register keyword. The function instead of calling it. Unfortunately, this also means that the compiler will provide no help in case of an error in the type of one of the parameters. Here is the definition of a proper compatible function, which reads the title of the window into a string, then adds it to a list box of a given form. Function getTitle, boolean, stdcall, vartext, string, begin set length, getWinDoText, 100, form callback, listbox 1, items. add, in toaster plus text, result true, end. The form has a list box covering almost its whole area, along with a small panel on the top hosting a button. When the button is pressed, the enum Windows API function is called, and the getTitle function is passed as its parameter. Procedure at form callback. btntitlesclick. The proc, enum Windows proc. Begin listbox 1. Items. Clear. uproc getTitle. Enum Windows. End. I could have called the function without storing the value in a temporary procedural type variable first, but I wanted to make clear what is going on in this example. The effect of this program is actually quite interesting, as you can see in figure 9.2. The callback example shows a list of all the existing main windows running in the system. Most of them are hidden windows you usually never see. Figure 9.2, the output of the callback example, listing the current main windows. A minimal Windows program. To complete the coverage of Windows programming and the Pascal language, I want to show you a very simple but complete application built without using the VCL. The program simply takes the command line parameter and then extracts information from it with the paramCount and paramster Pascal functions. The first of these functions returns the number of parameters. The second returns the parameter in a given position. Although users seldom specify command line parameters in a graphical user interface environment, the Windows command line parameters are important to the system. For example, once you have defined an association between a file extension and an application, you can simply run a program by selecting an associated file. In practice, when you double-click on a file, Windows starts the associated program and passes the selected file as a command line parameter. Here is the complete source code of the project. Program strparam. Use Windows. Begin show the full string message box 0, cmdline. strparam command line, megabytes OK. Show the first parameter if paramCount greater than 0 then message box. Single quote first strparam parameter, megabytes OK. Else message box. Single quote first strparam parameter, megabytes OK. End. The output code uses the MessageBox API function, simply to avoid getting the entire VCL into the project. A pure Windows program as the one above, in fact, has the advantage of a very small memory footprint. The executable file of the program is about 16 bytes. To provide a command line parameter to this program, you can use Delphi's run greater than parameters menu command. Another technique is to open the Windows Explorer, locate the directory that contains the executable file of the program, and drag the file you want to run onto the executable file. The Windows Explorer will start the program using the name of the dropped file as a command line parameter. Figure 9.3 shows both the Explorer and the corresponding output. Figure 9.3, you can provide a command line parameter to the strparam example by dropping a file over the executable file in the Windows Explorer. Conclusion. In this chapter we've seen a low-level introduction to Windows programming, discussing handles and a very simple Windows program. For normal Windows programming tasks, you'll generally use the visual development support provided by Delphi and based on the VCL. But this is beyond the scope of this book, which is the Pascal language. Next chapter covers variants, a very strange addition to Pascal type system, introduced to provide full OL support. Chapter 10 Variants. To provide full OL support, the 32-bit version of Delphi includes the variant data type. Here I want to discuss this data type from a general perspective. The variant type, in fact, has a pervasive effect on the whole language, and the Delphi components library also uses them in ways not related to OL programming. Variants have no type. In general, you can use variants to store any data type and perform numerous operations and type conversions. Notice that this goes against the general approach of the Pascal language and against good programming practices. A variant is type-checked and computed at runtime. The compiler won't warn you of possible errors in the code, which can be caught only with extensive testing. On the whole, you can consider the code portions that use variants to be interpreted code, because, as with interpreted code, many operations cannot be resolved until runtime. This affects in particular the speed of the code. Now that I've warned you against the use of the variant type, it is time to look at what it can do. Basically, once you've declared a variant variable such as the following varv, variant, you can assign to it values of several different types. v10, vhello, world, v45.55. Once you have the variant value, you can copy it to any compatible or incompatible data type. If you assign a value to an incompatible data type, Delphi performs a conversion, if it can. Otherwise it issues a runtime error. In fact, a variant stores type information along with the data, allowing a number of runtime operations. These operations can be handy but are both slow and unsafe. Consider the following example, which is an extension of the code above. I placed 3 edit boxes on a new form, added a couple of buttons, and then wrote the following code for the on-click event of the first button. Procedure at form 1. Button 1 click. Varv, variant. Begins 10. Edit 1. Text v. Hello, world. Edit 2. Text v. 45.55. Edit 3. Text v. End. Funny, isn't it? Besides assigning a variant holding a string to the text property of an edit component, you can assign to the text a variant holding an integer or a floating point number. As you can see in figure 10.1, everything works. Figure 10.1, the output of the variedist example after the assign button has been pressed. Even worse, you can use the variants to compute values, as you can see in the code related to the second button. Procedure at form 1. Button 2 click. Varv, variant. N, integer. Begin edit 1. Text. N integer 2. Vn. Edit 1. Text v. End. Writing this kind of code is risky, to say the least. If the first edit box contains a number, everything works. If not, an exception is raised. Again, you can write similar code, but without a compelling reason to do so, you shouldn't use the variant type. Stick with the traditional Pascal data types and type checking approach. In Delphi and in the VCL, variants are basically used for OL support and for accessing database fields. Variants in depth. Delphi includes a variant record type, var_data, which has the same memory layout as the variant type. You can use this to access the actual type of a variant. The var_data structure includes the type of the variant, indicated as type, some reserved fields, and the actual value. The possible values of the type field correspond to the data types you can use in OL automation, which are often called OL types or variant types. Here is a complete alphabetical list of the available variant types. Var array, var boolean, var by ref, var currency, var data, var dispatch, var double, var empty, var integer, var null, var lester, var single, var small, var string, var type, mask, var unknown, var variant. You can find descriptions of these types and the values in variants topic in the Delphi help system. There are also many functions for operating on variants that you can use to make specific type conversions or to ask for information about the type of a variant. Most of these type conversion and assignment functions are actually called automatically when you write expressions using variants. Other variant support routines actually operate on variant arrays. Variants are slow. Code that uses the variant type is slow, not only when you convert data types, but also when you add 2 variant values holding an integer each. They are almost as slow as the interpreted code of Visual Basic. To compare the speed of an algorithm based on variants with that of the same code based on integers, you can look at the speed example. This program runs a loop, timing its speed and showing the status in a progress bar. Here is the first of the 2 very similar loops, based on integers and variants. Procedure at form 1. Button 1 click. Vor time 1, time 2, data time. N1, N2, variant. Begin time 1 now. N1, 0. N2, 0. Progress bar 1. Position 0. While N1 less than 5 million to begin to N2 plus N1. Inc. If equals 0 then begin progress bar 1. Position N1 dive 50,000. Application. Process messages. End. We must use the result total N2. Time 2 now. Label 1. Caption format data time plus seconds. End. The timing code is worth looking at, because it's something you can easily adapt to any kind of performance test. As you can see, the program uses the now function to get the current time and the format data time function to output the time difference, asking only for the minutes and the seconds in the format string. As an alternative, you can use the Windows API's getDiscount function, which returns a very precise indication of the milliseconds elapsed since the operating system was started. In this example, the speed difference is actually so great that you'll notice it even without a precise timing. Anyway, you can see the results for my own computer in figure 10.2. The actual values depend on the computer you use to run this program, but the proportion won't change much. Figure 10.2, the different speeds of the same algorithm, based on integers and variants, as shown by the speed example. Conclusion. Variants are so different from traditional Pascal data types that I've decided to cover them in this short separate chapter. Although their role is in all programming, they can be handy to write quick and dirty programs without having even to think about data types. As we have seen, this affects performance by far. Now that we have covered most of the language features, let me discuss the overall structure of a program and the modularization offered by units. Chapter 11 Program and Units. Delphi applications make intensive use of units, or program modules. Units, in fact, were the basis of the modularity in the language before classes were introduced. In a Delphi application, every form has a corresponding unit behind it. When you add a new form to a project, Delphi actually adds a new unit, which defines the class for the new form. Units. Although every form is defined in a unit, the reverse is not true. Units do not need to define forms. They can simply define and make available a collection of routines. By selecting the file greater than new menu command and then the unit icon in the new page of the object repository, you add a new blank unit to the current project. This blank unit contains the following code, delimiting the sections a unit is divided into. Unit 1. Interface implementation end. The concept of a unit is simple. A unit has a unique name corresponding to its file name, an interface section declaring what is visible to other units, and an implementation section with the real code and other hidden declarations. Finally, the unit can have an optional initialization section with some startup code, to be executed when the program is loaded into memory. It can also have an optional finalization section, to be executed on program termination. The general structure of a unit, with all its possible sections, is the following. Unit initnum. Interface. Other units we need to refer to use ESA, B, C. Exported type definition type NU type equals type A definition. Exported constants cons 0 equals 0. Global variables var total, integer. List of exported functions and procedures. C++ programmers should be aware that the uses statement does not correspond to an include directive. The effect of a uses statement is to import just the precompiled interface portion of the units listed. The implementation portion of the unit is considered only when that unit is compiled. The units you refer to can be both in source code format or compiled format, but the compilation must have taken place with the same version of the Delphi. Procedure me proc. Implementation used, E. Hidden global variable var partial total, integer. All the exported functions must be coded procedure me proc. Begin. Code of procedure me proc end. Initialization optional initialization part. Finalization optional cleanup code. End. The uses clause at the beginning of the interface section indicates which other units we need to access in the interface portion of the unit. This includes the units that define the data types we refer to in the definition of other data types, such as the components used within a form we are defining. The second uses clause, at the beginning of the implementation section, indicates more units we need to access only in the implementation code. When you need to refer to other units from the code of the routines and methods, you should add elements in this second uses clause instead of the first one. All the units you refer to must be present in the project directory or in a directory of the search path. The interface of a unit can declare a number of different elements, including procedures, functions, global variables, and data types. In Delphi applications, the data types are probably used the most often. Delphi automatically places a new class data type in a unit each time you create a form. However, containing form definitions is certainly not the only use for units in Delphi. You can continue to have traditional units, with functions and procedures, and you can have units with classes that do not refer to forms or other visual elements. Units and scope. In Pascal, units are the key to encapsulation and visibility, and they are probably even more important than the private and public keywords of a class. In fact, as we'll see in the next chapter, the effect of the private keyword is related to the scope of the unit containing the class. The scope of an identifier is the portion of the code in which the identifier is accessible. The basic rule is that an identifier is meaningful only within its scope, that is, only within the block in which it is declared. You cannot use an identifier outside its scope. Here are some examples. Global hidden variables. If you declare an identifier in the implementation portion of a unit, you cannot use it outside the unit, but you can use it in any block and procedure defined within the unit. The memory for this variable is allocated as soon as the program starts and exists until it terminates. You can use the initialization section of the unit to provide a specific initial value. Local variables. If you declare a variable within the block defining a routine or a method, you cannot use this variable outside that procedure. The scope of the identifier spans the whole procedure, including nested routines. The memory for this variable is allocated on the stack when the program executes the routine defining it. As soon as the routine terminates, the memory on the stack is automatically released. Global variables. If you declare an identifier in the interface portion of the unit, its scope extends to any other unit that uses the one declaring it. This variable uses memory and has the same lifetime as the previous group. The only difference is in its visibility. Any declarations in the interface portion of a unit are accessible from any part of the program that includes the unit in its uses clause. Variables of form classes are declared in the same way, so that you can refer to a form from the code of any other form. Of course, it's poor programming practice to declare everything as global. Besides the obvious memory consumption problems, using global variables makes a program less easy to maintain and update. In short, you should use the smallest possible number of global variables. Units as namespaces. The uses statement is a standard technique to access the scope of another unit. At that point you can access the definitions of the unit. But it might happen that two units you refer to declare the same identifier. That is, you might have two classes or two routines with the same name. In this case you can simply use the unit name to prefix the name of the type or routine defined in the unit. For example, you can refer to the compute_total procedure defined in the given totals unit as totals. Compute_total. This should not be required very often, as you are strongly advised against using the same name for two different things in a program. However, if you look into the VCL library and the Windows files, you'll find that some Delphi functions have the same name as some Windows API functions available in Delphi itself. An example is a simple beep procedure. If you create a new Delphi program, add a button, and write the following code. Procedure form 1. Button 1 click. Begin beep. End. Then as soon as you press the button you'll hear a short sound. Now, move to the uses statement of the unit and change the code from this. Use windows, messages, sysutils, classes. To this very similar version. Use sysutils, windows, messages, classes. If you now try to recompile this code, you'll get a compiler error, not enough actual parameters. The problem is that the Windows unit defines another beep function with two parameters. Stated more generally, what happens in the definitions of the first units you include in the uses statement might be hidden by corresponding definitions of later units. The safe solution is actually quite simple. Procedure at form 1. Button 1 click. Begin sysutils. Beep. End. This code will compile regardless of the order of the units in the uses statements. There are few other name clashes in Delphi, simply because Delphi code is generally hosted by methods of classes. Having two methods with the same name in two different classes doesn't create any problem. The problems arise only with global routines. Units and programs. A Delphi application consists of two kinds of source code files, one or more units and one program file. The units can be considered secondary files, which are referred to by the main part of the application, the program. In theory, this is true. In practice, the program file is usually an automatically generated file with a limited role. It simply needs to start up the program, running the main form. The code of the program file, or Delphi project file, can be edited either manually or by using the project manager and some of the project options related to the application object and the forms. The structure of the program file is usually much simpler than the structure of the units. Here is the source code of a sample program file. Program project 1. Uses forms, unit 1 and unit1.pas. Begin application. Initialize. Application. Create form. Application. Run. End. As you can see, there is simply a uses section and the main code of the application, enclosed by the begin and end keywords. The program's uses statement is particularly important, because it is used to manage the compilation and linking of the application. Conclusion. Units were the Pascal technique for module programming. Even if they were later followed by objects and classes, they still play a key role for encapsulation, for the definition of some sort of namespaces, and for the overall structure of Delphi programs. Also, units have influence on scope and global memory allocations. Oh. The close file operation should typically be done inside a finally block, to avoid leaving the file open in case the file handling code generates an exception. Actually, file-based operations generate exceptions or not depending on the $I compiler settings. In case a system doesn't raise exceptions, you can check the result global variable to see if anything went wrong. Chapter 12 Files in the Pascal language. One of the peculiarities of Pascal compared with other programming languages is its built-in support for files. As you might recall from Chapter 2, the language has a file keyword, which is a type specifier, like array or record. You use file to define a new type, and then you can use the new data type to declare new variables. Type in file of integers. Var file1, in file. It is also possible to use the file keyword without indicating a data type, to specify an untyped file. Alternatively, you can use a text file type, defined in the system units to declare files of ASCII characters. Each kind of file has its own predefined routines, as we will see later in this chapter. Routines for working with files. Once you have declared a file variable, you can assign it to a real file in the file system using the assignFile method. The next step is usually to call reset to open the file for reading at the beginning, rewrite to open it for writing, and append to add new items to the end of the file without removing the older items. Once the input or output operations are done, you should call close file. As an example, look at the following code, which simply saves some numbers to a file. Type in file of integers. Var file1, in file. Begin assignFile. Rewrite. Write. Close file. End. Delphi includes many other file management routines, some of which are includes in the list below. Append file close flash assignFile file create take a block red file data emia result blockfilexistsmkdir. Change file ext file edit red close file edit data read on data tomato file date file open rename delete file pos rename file disk free file read reset disk file search rewrite file secondary on file set into seek erase file set data seek expand file nm file seek on extension. Racked file ext file write set ext buff extract file nm find closet trinket extract file path find first write file each find next write down. Not all of these routines are defined in standard Pascal, but many of them have been part of Borland Pascal for a long time. You can find detailed information about these routines in Delphi's help files. Here, I'll show you 3 simple examples to demonstrate how these features can be used. Handling text files. One of the most commonly used file formats is that of text files. As I mentioned before, Delphi has some specific support for text files, most notably the text file data type defined by the system unit. Ignoring the fact that Delphi's string lists can automatically save themselves to a file, you could easily save the content of a string list to a text file by writing the following code in which the file name is requested to the user. Using Delphi's save dialog component. Var output file, text file. Integer. Begin choose a file of save dialog 1. Execute then begin output the text to a file assignFile. Rewrite. Try save listbox data to file for I0 to listbox 1. Items. Count -1 to write down. Finally close file. End. A text file converter. Up to now we've seen simple examples of creating new files. In our next example, we'll process an existing file, creating a new one with a modified version of the contents. The program, named filter, can convert all the characters in a text file to uppercase, capitalize only the initial word of each sentence, or ignore the characters from the upper portion of the ASCII character set. The form of the program has 2 read-only edit boxes for the names of the input and output files, and 2 buttons to select input and output files using the standard dialog boxes. The form's lower portion contains a radio group component and a bitmap button to apply the current conversion to the selected files. The radio group has 3 items, as you can see from the following portion of the form's textual description. Object radio group 1, radio group caption equals conversion. Items. Strings equals. And uppercase. Capitalize and sentences. Remove symbols. The user can click on the 2 buttons to choose the names of the input and output files, displayed in the 2 edit boxes. Procedure at form 1. Button 1 click. Begin if open dialog 1. Execute then edit 1. Text open dialog 1. File name. End. The second button activates the save dialog 1 dialog box. The real code of the example is in the 3 conversion routines that are called by the bitmap buttons on click event handler. These calls take place inside a case statement in the middle of the convert bit buttons on click handler. Case radio group 1. ID mindex of 0, conv upper. 1, conv capitalize. 2, conv symbols. End. Once again, you can see the entire source code among the download files. Before calling one of the conversion procedures, the convertbitbtnclick method displays a dialog box with a progress bar component to show the user that the conversion is taking place. This method does most of the work related to handling the files. It opens the input file as a file of bytes the first time, so that it can use the file size procedure, which is not available for text files. Then this file is closed and reopened as a text file. Since the program opens two files, and each of these operations can fail, it uses two nested try blocks to ensure a high level of protection, although using the standard dialog boxes to select file names already provides a good confirmation of file selection. Now, let's take a look at one of the conversion routines in detail. The simplest of the three conversion routines is convupper, which converts every character in the text file to uppercase. Here is its code. Instead of being connected to a physical file, a Pascal file type variable can be hooked directly to the printer, so that the output will be printed instead of being saved to a file. To accomplish this, simply use the assign print procedure. For example, in the code above you could replace the line assign file with the line assign print procedure at form 1. Convupper varch char position long int begin position 0 while not a off do begin red ch upcase right inc convert form progress bar 1 position 100 dive file length application process messages end. This method reads each character from the source file until the program reaches the end of the file. Each single character is converted and copied to the output file. As an alternative, it is possible to read and convert one line at a time using string handling routines. This will make the program significantly faster. The approach I've used here is reasonable only for an introductory example. The conversion procedure's actual code, however, is complicated by the fact that it has to update the dialog box's progress bar. At each step of the conversion, a long integer variable with the current position in the file is incremented. This variable's value is used to compute the percentage of work completed, as you can see in the code above. The conversion procedure for removing symbols is very simple. While not a off do begin red, if ch less than chr then right. The procedure used to capitalize the text, in contrast, is really a complex piece of code, which you can find in the code of the example. The conversion is based on a case statement with 4 branches. If the letter is uppercase, and it is the first letter after an ending punctuation mark, it is left as is. Otherwise, it is converted to lowercase. This conversion is not done by a standard procedure, simply because there isn't one for single characters. It's done with a low-level function I've written, called lowcase. If the letter is lowercase, it is converted to uppercase only if it was at the beginning of a new sentence. If the character is an ending punctuation mark, period is set to true. If the character is anything else, it is simply copied to the destination file, and period is set to false. Figure 12.1 shows an example of this code's effect. It shows a text file before and after the conversion. This program is far from adequate for professional use, but it is a first step toward building a full-scale case conversion program. Its biggest drawbacks are that it frequently converts proper nouns to lowercase, and capitalizes any letter after a period. Figure 12.1, the result of running the filter example's capitalized conversion. Saving generic data. In addition to using text files, you can save other data types to a file, including integers, real numbers, arrays, and records. Using a custom file type instead of a text file may be an advantage because it might take less space. But this approach won't let the user browse through the files using a text editor. How do you save a series of integers to a file? First you have to define a file as shown. Save file, file of integer. Then you need to assign the real file to the file variable, open the file, operate on it, and close it. For example, the following code saves all the numeric data collected in a 5x4 string grid. Assign file. Rewrite. Try. For I1 to 5 do for J1 to 4 do begin value strtointdef trim. String grid 1. Cells 0. Right. End. Finally close file. End. To save the data to a file, the program saves each value of the string grid. To accomplish this, the program uses 2 nested for loops to scan the grid. Notice the use of the temporary value variable. The write and read procedures require a parameter passed by reference, so you cannot pass the property of a Delphi component, since it doesn't correspond directly to a memory location. Of course, the data should be read in the same order it is written, as you can see in the open one-click method. Assign file. Reset. Try. For I1 to 5 do for J1 to 4 do begin read. String grid 1. Cells in toaster. End. Finally close file. End. From files to streams. Although direct handling of files, using the traditional Pascal language approach is certainly still an interesting technique, I strongly urge you to use streams to handle any complex files. Streams represent virtual files, which can be mapped to physical files, to a memory block, to a socket, or any other continuous series of bytes. You can find more on streams in the Delphi help file and in my Mastering Delphi book. Conclusion. At least for the moment, this chapter on files is the last of the book. Feel free to send me feedback as suggested in the introduction, sending me your comment and requests. If after this introduction on the Pascal language you want to delve into the object-oriented elements of Object Pascal in Delphi, you can refer to my printed book of the series Mastering Delphi. As I mentioned earlier, buying one of my printed books and donating me some cash for this book is the best way to support its future development, so that other programmers can benefit from this effort. Helping me with the update is another very good way to contribute. For more information on the latest edition of Mastering Delphi and more advanced books of mine, you can refer to my website. The same site hosts updated versions of this book and its examples. Keep also an eye for the companion book Essential Delphi. Happy coding. Appendix: a glossary. His is a short glossary of technical terms used throughout the book. They might also be defined elsewhere in the text, but I've decided to collect them here anyway, to make it easier to find them. Heap. The term heap indicates a portion of the memory available to a program, also called dynamic memory area. The heap is the area in which the allocation and deallocation of memory happens in random order. This means that if you allocate 3 blocks of memory in sequence, they can be destroyed later on in any order. The heap manager takes care of all the details for you, so you simply ask for new memory with getMem or by calling a constructor to create an object, and Delphi will return you a new memory block. The heap is one of the 3 memory areas available to an application. The other 2 are the global area and the stack. Contrary to the heap, global variables are allocated when the program starts and remain there until it terminates. For the stack, see the specific entry in this glossary. Delphi uses a heap for allocating the memory of each and every object, the text of the strings, for dynamic arrays, and for specific requests of dynamic memory. Windows allows an application to have up to 2 GB of address space, most of which can be used by the heap. Stack. The term stack indicates a portion of the memory available to a program, which is dynamic but is allocated and deallocated following specific order. The stack allocation is LIFO, last in first out. This means that the last memory object you've allocated will be the first to be deleted. Stack memory is typically used by routines. When you call a routine, its parameters and return type are placed on the stack. Also, the variables you declare within a routine are stored on the stack, so that when the routine terminates they'll be automatically removed. The stack is one of the 3 memory areas available to an application. The other 2 are called global memory and heap. See the heap entry in this glossary. Delphi uses a stack for routine parameters and return values, for local routine variables, for Windows API function calls, and so on. Windows applications can reserve a large amount of memory for the stack. In Delphi you set this in the linker page of the project options, however, the default generally does it. If you receive a stack full error message, this is probably because you have a function recursively calling itself forever, not because the stack space is too limited. More terms for the glossary. Dynamic. Static. Virtual. Memory leak. Painting. Literal. Array. API. Class reference. Class method. Parent. Owner. Self. Appendix B. Examples. This is a list of the examples which are part of Essential Pascal and available for download. Chapter 3. Register, resource strings range, ordinal types ranges to time manipulation. Chapter 4. GPF, general protection faults with null pointers. Chapter 5. If-dist, if statements loops, for and while statements. Chapter 6. Opener, open array parameters double, simple procedures proctype, procedural types overdev, overloading and default parameters. Chapter 7. Stref, strings reference counting longster, using long strings fntist, formatting examples. Chapter 8. Dinar, dynamic arrays WANDL, Windows handles callback, Windows callback functions strparam, command line parameters. Chapter 10. Varietist, simple variant operations vary speed, the speed of variance,